Okay, so welcome again to this first slices meeting. Let me share my screen for a moment. Okay, so the slices first industry day will run until 2 o'clock set. We will try to keep this schedule. The agenda for this meeting is this. You can find it also in the chat. So we will try to keep the presentation time to 15 minutes with 5 minutes questions. So please keep the time if you can do that, because there are a lot of presentations, so we need to finish at 2 sets. So I propose to have 1 or 2 questions per presentation after its presentation, so that we keep this time. So if you have more questions than that, I suggest that you can contact either the speaker by mail or me personally, so that I can direct the questions to the right people in slices. So that's all for me. I think I will hand over to Serge to give you the view and the vision of slices, and I hope that you enjoy this workshop. Thank you for coming again. Slices.
Thank you, Konstantinos.
Stop sharing. Okay, you're welcome.
So good morning to everyone. Thanks for joining. I mean, despite the fact that maybe today is not the best time, as some are on vacation, but as it will be recorded, we expect that this will be useful for a larger community. So the idea here, as mentioned by Konstantinos, is to give you some highlights about slices and how this is of course, valuable for the research community, but also with quite important ties with the industry. So slices is meant to support the discovery process with respect to digital infrastructures. So as you know, but maybe it is a bit forgotten, there is no digital transformation of the society without an efficient, reliable, secured, and scalable digital infrastructure. So of course, a lot of people are currently working on the design of such an infrastructure, but obviously it's becoming more and more difficult to provide evidence, and therefore the objective of slices is to provide a scientific instrument to support the research in this domain. And to convince you that this is an important endeavor, of course, we are not the only one with this objective. There are already important initiatives that have been developed worldwide, and especially in the US, very important development regarding the beyond 5G and 6G perspectives. So with the NSF Power initiative, for instance, Fabric, Bridges, Colosseum, all of them basically are organized mostly with the research community, but also with a strong support from industry in order to get prepared to develop a competitive advantage with respect to those digital infrastructures. Likewise, in China, they have this big CHENI initiative. And in Europe, certainly you're aware of the 5G ICT 17, 19, 52 project. and that there is a specific track within the EU SNS joint initiative, which is stream C, dealing with, again, those facilities. What is really important as well is to understand that it's not only a development from the usual stakeholders, but also with respect to important initiatives taken by industry and more specifically the hyperscalers like Google, Amazon, and so on. They have their own large-scale infrastructure, which is mixing production and somehow data collection, which give them quite a competitive advantage with respect to exploring the design space of the future infrastructures. But there are also opportunities, because we observe since a couple of years now important initiative, which is mostly driven by open source flavor, like ONAP, ORAN, Open Interface. And we believe that those will certainly provide us with opportunities. So you could consider that slices is just yet another testbed, as we see a lot of testbed facilities, demonstrators that are developed here and there with respect to specific design questions. But of course, there are always issues with those solutions, because it's very fragmented and it's very difficult to sustain. So the academic community dealing with wireless systems, dealing with networking protocol, distributed systems and algorithms, cloud, and so on, decided finally, after many years of design and operation of different type of testbeds, to target a specific instrument which exists at the European level, but you will see also with a strong engagement of the member states. And this framework is called S3, European Strategy Forum on Research Infrastructures. So S3 is the place basically where in Europe we incubate, prepare future medium to large scale scientific instruments, of course in many disciplines and mostly for years in the fundamental disciplines. So you could see here, without going into the details, that they are in S3 working groups dealing with energy, health and food, environment, social and cultural innovation, physical science and engineering, of course. But until very recently, there were no group dealing with data, computing, and digital research infrastructures. Mostly because up to there, it was considered that those infrastructures, be it compute or networking or storage, were basically production infrastructure to support e-science. But none of them were dedicated to basically support the design of digital infrastructures or digital science in general. So in 2018, fortunately, S3 decided to open a new working group where we could fit this idea of developing a scientific instrument for the design of research infrastructures. So S3, of course, is a framework, so you have to fit into this framework. It is meant to sustain those large-scale instruments in the long term. Because, for instance, if you want to question whether the Higgs boson exists, then you have to design an infrastructure that will last for many years in order to provide a sustainable framework for the researchers to basically address those scientific questions. So you have to go into what you see here, a life cycle approach of the research infrastructure, where you start first to mobilize the community and try to raise awareness with respect to the stakeholders. And then you move into the design space where you try to collect what is necessary in order to provide confidence with respect to the capacity that you will have to build the facility. And then you move into the preparation phase in order to prepare the design, the specification, the organization, the governance, the funding, and so on. And then you start to implement, you operate, and then you dismantle if you have a facility up and running. So those phases have milestones, and you have to satisfy key minimum requirements to move from one phase to another. So of course, it's a completely different framework than the one that, for instance, we have been using in the past with Horizon 2020 or Horizon Europe. But it provides this capacity to build something which is really to the scale and the sustainability that we are expecting for those type of questions. So we're very happy that we succeed in 4 years, which is quite tricky, to have slices on the S3 2021 roadmap, meaning that now we have passed the first phase and we are moving along the different phases and steps that I have mentioned earlier. What do we plan to achieve with this? So we expect to benefit from the evolution of the knowledge and the solutions, methodology that are developed within networking, wireless, cloud, and HPC. With respect to the network is becoming the computer that was planned and expected a long time ago through this statement from John Gage, but it's happening now. And as mentioned as well by Nick McCrone at an ONF presentation 2 years ago, but Nick now, as you know, has moved to Intel, promoting again this idea that the network is just becoming a programmable platform. And this is exactly the type of spirit that we have developed in many of the test beds that we designed in the past. And we believe that this will provide us with the capacity to basically offer interesting and advanced services to the community. So Slices is meant to become a fully controllable, because it's an instrument, so you need to control precisely the experiments and collect the data and make this data available at large. I'll come back to that a bit later. It has to be programmable, of course, it's virtualized, and it's a test platform that we expect to be fully open according to the FAIR principles. So you see here that thanks to the success entering the S3 roadmap, we already have mobilized quite a large set of support. You see that Slices now received the political support, so meaning from the national ministries of 12 member states that you could see here, as well as the support from organization, let's say, with another 3 member states. And the local facilities that we have in Slices already, for 5 of them, are on the national roadmaps for research infrastructure. So it's a quite important support to build the facility in the long term. Of course, the process for integrating new contributors is open, and we expect, of course, to make Slices as inclusive as possible. So I won't go into the details, but what you see here that beside the political support, of course, we have a strong engagement of the community, mostly from academia, but you see, as well here, a strong support and intent to participate from industry, large industry, SMEs, as well as different clusters, and national research networks with a strong tie with international cooperation. Because this is a community development, and of course it's important for us to leverage slices through an international cooperation. Time-wise, of course, because we are now in the design phase, it means that slices doesn't exist. But nevertheless, as you have seen in this program, you will have the possibility to access facilities that are up and running now in the different member states, and that will contribute globally to the development of the slices facility. But as you can see here, we are still now in the design phase, basically, which is going to close in a few months, entering the preparation phase in September, where the preparation phase is dedicated to, of course, continue to think about the design and deployment, but to put together the pieces that are necessary to drive and steer such a large initiative. And for instance, of course, the governance, there will be a legal entity to organize slices, as well as the office, the human resources, and of course the engagement of the different stakeholders. And then we will have a progressive opening. So it's not like in other sciences where you can access a telescope only when it is fully operational. In slices, we'll have the possibility to open gradually, depending on the progress with respect to the engagement of the different stakeholders. So you see that slices with operation, we could start in early 2024 to provide access to slices with the main components that will be enriched progressively and that will be complemented as we move, depending on the most important research questions and technologies that we can integrate. So I'll go very quickly on the governance, but what is important to understand is that the organization of slices as within S3 mean that it's a joint investment strategy from the member states and from the European Commission. So it's important also to continue to mobilize the political support and the engagement of the stakeholders within each node, meaning each member state that is currently involved in slices. So it's a distributed infrastructure, so meaning that we have nodes in different countries that organize themselves as they want. Of course, the design has been organized in order to nicely complement what is deployed in the different member states and what is shared globally. And there is a strong control and coordination, which is developed at the central node, central office, that is basically hosting the governance as well as hosting the shared components of slices. So, of course, we ambition to address a quite broad set of research topics that you can see in this slide, ranging from advanced wireless platforms and many important questions that are being discussed now with respect to beyond 5G and 6G, but also all the topics related to AI, ML integration within the future solutions, smart infrastructure operation and management, the ability of the system to provide a self-manageable and self-controlled environment, as well as the design and validation of new distributed infrastructure and hyper-converged infra. So all those concepts related to the deployment of functions from the core to the edge and the far edge, including the mobile equipment, in order to provide advanced services and advanced functionalities. Of course, likewise, issues related to energy efficiency and carbon footprint, as you know, are becoming of utmost importance, and we really want to support this kind of development. as well as security and robustness and privacy at large. So in slices, you will have nodes that will be more dedicated to core infrastructure, for instance, including aspects related to optical, related to core distribution of intelligence and other characteristics, as well as edge, and as I mentioned earlier, far edge and IoT. And we expect to have an important liaison with external clouds because it will be important for us to provide those kind of synergies. What is important is because slices is positioning itself in S3, we don't want to limit slices to an infrastructure, which of course is already quite valuable, but we want to position slices also as a support to the full research life cycle. So what it means, and unfortunately we have seen this in the COVID episode, that it's important that the community will benefit from the experience of others, and especially through the capacity to share data and make this available to the community in order to speed up the discovery process and enable reproducibility. So in slices, we will collect data that is specific, let's say, to the runtime of slices, but we will also collect the data from the experiments if allowed by the experimenters. Of course, the data is shared as it's as open as possible, but as the Commission said, as close as necessary. So privacy will be enforced for those experiments that don't want to share the data. And this will be shared with respect to an important development that we have in order to provide interoperability with another important initiative of the Commission, which is named EOS, the European Open Science Cloud. And again, the objective in there is to provide to the community access to data that has been extracted from the experiments and that are producing results and outcomes, but as well as to source code that, for instance, have been used to illustrate and aggregate those data, as well as, of course, the engagement of the community with different type of initiatives, like training, for instance, that we believe is instrumental with respect to capacity building. So, indeed, slices is moving through the process of S3, which is mostly addressing the most important scientific questions and designing an instrument to research those important scientific questions. But nevertheless, and of course, obviously, because of the topic that we are addressing, in slices, the community is always keen, and even more than keen, strongly motivated to develop tight ties with industry. As you have seen, we have a strong support letters from a large and broad set of industry players. In the past, if we look, and you will see certainly some of those in the presentation today, but if we look at the experiments that are using our facilities, you will see that we have about 20% of the experiments that comes from industry for research purposes, of course, even if industry in number of users is more around 50% with respect to the global participation. So still, it's important and it provides the capacity for large industry, but also small industry and startup to benefit from an instrument that is very advanced with respect to what type of questions they are raising. So we have developed already good synergies with different type of organizations and especially, for instance, most lately, the SNS JIU. But of course, also with other initiatives, and we are most welcome to open liaison with a different type of collective development that is mostly driven by industry. So, in a nutshell, we believe that there are strong opportunities for industry to contribute and participate and use slices. We have in our different organizations taking care of the development of slices industry, which is involved, and also from different type of organizations. It's possible for industry, of course, to provide also contributions in kind with respect to the possibility to experiment with some specific instrumentation. We are very keen also to consider verticals. So even if we address core networking and distributed system technologies, the verticals are very important, and we would like to see some end-to-end experiments on the facility. And as I mentioned earlier, Slices is open. We have an access which is known as market access, which is available for industry with the specific constraint that we could consider regarding an access with, let's say, privacy or other type of issues related to access to data. So therefore, as a conclusion, we are very happy to have this workshop today in order to raise awareness about the fact that this initiative is going to build over time. But already we're happy to open a discussion with industry and to better understand what is the demand and how the demand is evolving in order to make sure that we can match the demand and we can really engage very nicely together with industrial partners in the development of slices. So what you will see today, as it was mentioned by Konstantinos, is not slices for the reason that I mentioned, but those are facilities and test beds that are currently available and operated mostly by organizations that are within slices. And of course, we are going to benefit from this long experience of designing, deploying, and operating this type of facility. So thanks a lot. Again, if you would like to get more information about slices, there is a website where you can see most of the information. And of course, we are always available to open direct liaison in case you have specific questions. Thanks for listening. And again, I wish you a very nice day. And again, thanks to Konstantinos and the colleagues for organizing this nice initiative. And I hand over to you, Konstantinos.
Okay, thank you. Thank you, Serge. Thank you very much for your speech. The next presentation is about transnational access, open call, and the evaluation process for experimenting on slices infrastructures. The next open call is about to become available, and Peter, I believe that can give us more information about that. Peter, I hand over to you.
Thank you. Good morning, everybody. I'm trying to share my screen. Is it okay? Can you see it?
Yes, yes.
Great. Okay, so good morning, everybody. I'm going to talk about the transnational access procedure, which is a very important aspect of using the slices infrastructure. It has actually two major part. One is the open core by which people can apply for the usage. And the other one is, of course, the evaluation process by which we select those applicants who can really start to do the experiment on the slices infrastructures. So I'm going to talk about these two aspects of our infrastructure usage. So considering the background, as you heard from Serge's presentation, the Slices S3 program actually builds an international IT infrastructure, a distributed IT infrastructure, in order to enable IT-oriented research and experiments. Now, currently, we have these 12 infrastructures involved in the program. If you go to the web page, you can see this is a screenshot of the web page. So you can see these 12 different organizations which provide the infrastructures. And if you click on one of these organizations, then you will see the actual infrastructure which is provided by this organization. So of course, I don't want to go to the details, but anyone who are interested in any of these infrastructure can go to the web page and access at least the information on the infrastructure. Now, considering the objectives of the transnational access, this is in order to do real experiment on these infrastructures, and it can be done in two ways. One is to remotely use the infrastructures. The other one is personally go there and do the experiment on the spot. In any case, if you want to use the infrastructure based on these transnational access experiments, then you have to go through 4 phases. The first phase is which is a kind of application phase for which we created and released an open call. It was opened this April on the 27th. And then once you applied for the usage, then the next phase is coming, the evaluation phase. Then this is our task in the project to evaluate the applications. And once your application is accepted, then you enter to the third phase, which is the usage of the facilities. And finally, of course, it is very important to get some review and feedback from the experimenters and the host, how successful the experiments were, was any positive or negative experience, whatever. So indeed, feedback is extremely important, both for us and for the future experimenters. So in this talk, I'm trying to explain you the first 2 phases, because these are the current and coming phases. So it's very important that everybody should be aware what can be done and how it is done in the coming months. So first of all, about the open call. As I mentioned, the open call was released on the 27th of April. And of course, it can be accessed on the Slices webpage. So if you go to this webpage, you can get practically all the information I'm going to present you now. But of course, it is good if I summarize the most important aspects of this open call. Another important point, of course, is the deadline, which is 10th of June. Unfortunately, it's quite close. So I urge everybody who are going to consider to submit a proposal to do it quickly, because the deadline is coming soon. Now, considering the infrastructures, I already showed you that we have 12 infrastructures in the project, but in this first experiment, only 7 of them will support the experimenters. And here you can see these infrastructures. I listed them. So first of all, 5-tonic from India, in Madrid, Spain. Then the 5G test network infrastructure from Finland. Actually, it has 2 different locations, Oulu, Sodankila, and Tampere. The next facility is LKH Cloud, which is from Hungary. Then Iot Lab infrastructure from Belgium. Again, with 2 locations, one is Antwerp and one in Gent. Then Anitos from Volos, Greece. Then Open 5G Lab from Sophia Antiopolis, France. And finally, Slices PL from PSNC Poznan, Poland. So these are the 7 infrastructures. Of course, you can get the details on the web page as I showed you before. And you can select any of them if you want to do an experiment, or you can select even more, 2 or 3 of them if you like, and you would like to use them together. So there's not a problem to do that. In order to apply for the experiment, you have to fill in an application template, and just very quickly I try to summarize the major points in the template. So first of all, we need a kind of project summary where you describe the proposed work, what you actually would like to do in the experiment. Then in section B, you give a bit more details, what you are going to do, what is the concept and objectives of your experiment, what would be the business impact, what is the state of the art concerning the work you are going to do in the experiment, and what is the actually applied methodology and the associated work plan. Then you have to actually point out which are those facilities you would like to use. So one of those 7 or several of those 7 should be given here. Then in the next section, you have to give your background and qualifications. So this is very important for us to judge your ability, whether you can really carry out this experiment or not. And then comes the expected feedback to Slices SC. As I mentioned earlier, feedback is extremely important for us and for the future users. So this is an important point as well. And then, of course, the future plans with your experiment and future plans, your activity on Slices and so on. And finally, financial issues also important, especially if you want to go, for example, personally to the infrastructure and you need some kind of a travel budget, then Slices can help you. So this is more or less the outline of the application form. And this is not a big deal. You can see that overall maximum 7 pages, what you can write. So in fact, you can be done quite quickly. Even the deadline is close, you are not certainly not in a position of missing this opportunity, because quickly you can create these 7 pages if you like. Now I'm going to switch to the evaluation process. It is also very important when you write this application, you should understand how, based on which criteria this will be evaluated. Now, first of all, the submitted applications will be collected on the Slices web page. And the evaluation process itself will consist of 4 steps. First of all, we are going to check the eligibility using so-called eligibility form. Then we are going to check the technical feasibility. I will explain immediately what are these feasibility criteria in both aspects. So the second one is the technical assessment form, which is used to judge the technical feasibility of your application. And then comes the scientific evaluation using the scientific evaluation form. And then based on this assessment evaluation, finally a decision will be done, and then you will be notified whether your application is accepted or not. Of course, all these forms will be available on the Slices webpage, so everybody can look at them and understand how this evaluation process will go on. Now, I'm trying to show you the process using some small figures to understand how it is actually done. So when the application forms are submitted via the web page, then in the first step, SZTAKI is going to check the eligibility for every applications. And for those applications where we find that they are really applicable from the point of view of eligibility, these applications will be passed to those infrastructure managers who are actually the target infrastructures in the given experiments. And in the second phase, these technical feasibility will be checked by the infrastructure managers and of course their experts. And at the end of this second phase, we will know which are those applications which are really applicable from the technical point of view. They can be really done on the target infrastructure. And these applications are passed forward to the third step, to the user committee. Now, coming back to the first steps, in the first step, we actually fill in the eligibility form for every application. And this is the criteria we are going to check in the eligibility form. So first of all, the user group leader and the majority of the users must work in a country other than the country where the installation is located. So you have to use another country's infrastructure, not an infrastructure in your country. This is the main message here. Only user groups that are allowed to disseminate the results and the knowledge they have generated under the action may benefit from the access free of charge. So if you are not allowed to disseminate your results during the experiment, unfortunately, you are not eligible to use the facilities. Obviously, we are very much interested in to disseminate all the results which are collected during the experiment. That's why this second criteria is very important. Also, very important that the user groups must agree to comply with the slices data policy. I'm sure this is understandable. And finally, access for user groups with a majority of users not working in an EU. So it means that not just EU countries, members, citizens can submit proposals. Researchers from outside Europe can also submit, but in this case, the usage of the time units, which is provided by the grant, maximum 20% of the available time units can be used for this kind of experiments. Okay, so these are checked in the first phase, and then those which eligible will be passed to the second step. And in the second step, we check the technical eligibility by the infrastructure managers. And here are the technical assessment criteria. So first of all, we check the technical feasibility, which is the adequacy with the facility characteristics. Here we check if the requested capacity is in line with the capacity of the infrastructure, the characteristics of the work is really fitting to the characteristics of the infrastructure and so on. The second aspect is the level of preparedness of the project. So how well your project is prepared to run the experiment on this particular infrastructure. And finally, scheduling and planning is also very important. We have to check the time frame, whether this is realistic on this particular infrastructure or not. So once you pass these two eligibility check, you enter to the third phase, which means that your application is going to be passed to the user community, user committee. And then the user committee is going to allocate for every application 2 different evaluators. And these are now scientific evaluation, which is going to happen. And either internal evaluators will be allocated or external evaluators. Obviously, the internal evaluators are SLICE's project members. Meanwhile, the external evaluators are user committee members. The task of the evaluators in this phase is to fill in the scientific assessment form. And here is the form. So here you can see that we have 8 different criteria. For each, we can give marks from 0 to 5. And for each, the threshold is at least you have to reach mark 3. And the different aspects have different weight. 3 of them have double weight, and the other ones have simple weight. Now let's go through research and scientific innovation and motivation. This is obviously very important. So the weight here is 2. So we are going to double the points you collect here. The same is true for research and scientific relevance. And then comes the clarity and methodology. The weight is 1. Socio-economic impact and sustainability of the result, again, weight 1. Scale and complexity of the experiment, weight 1. And now comes relevance for slices, weight is 2. So this, you should be very careful and emphasize when you submit your proposal why this is relevant for slices, because it has a very significant weight too. And then comes the possible future follow-up experiments criteria, and finally the technological expertise and quality. So overall, based on this, you will get a total score, and then when all these evaluation forms are collected, finally the user committee will decide which experiments are accepted and which are rejected. So the applicants will be notified, and those applications which are accepted can start the preparation, and then actually they can start the experiment from September. Okay, so I'm just going to summarize the major points from the whole process. So very important that we need just a short application, maximum 7 pages. The deadline is very close, so please do it quickly if you want to apply. Every information is on the slices web page, so if you need any additional information, you will get that information in the web page. The evaluation process itself is going to be very fast. Actually, we are going to evaluate in 3 weeks, but it will be very thorough. As you have seen, we allocated 4 different phases for evaluating the proposals. The applicants will be notified by 30th of June, so that's end of June. It will be, as I mentioned, a really fast process. And then successful applicants can start the experiments in September this year. And very important, as Serge mentioned, the companies are very welcome. So company researchers are also eligible to submit applications, and we are very happy to accept these applications. And finally, I would like to say thanks to Stavroula Maglavera, who has got a major contribution to all the processes presented here. And she also gave me many helps in organizing the open call. So thank you very much.
Okay, thank you, Peter. Thank you very much. Let's move to the next presentation, which will come from the Technical University of Munich. It concerns the POS framework, methodology, and toolchain for reproducible network experiments. Sebastian, I hand over the mic to you.
Okay, is everything visible? So am I understandable and the slides are visible?
Yes, yes, yes.
Okay, then let me start. So my talk today will be about the POS framework, a methodology and toolchain for reproducible network experiments. This was joint work with my colleagues Dominik Scholz, Henning Stubbe, Erik Hause, and Georg Karle. So first of all, typically everyone agrees that reproducibility in research is a highly important topic. And the best solution we have come up with so far is this. These are reproducibility badges that can be awarded to papers that go the extra mile and try to make their research understandable and so more reproducible for others. However, if we consider these 2 badges and the whole story behind them, so there were 2 workshops back in 2003 and one in 2017 that had the topic of reproducibility in mind. However, the problems more or less remained the same over 14 years. So there wasn't much progress in that area. And so these badges are still the best thing which we currently have. However, even these batches have their problems. So for instance, they are, you need you need to put a lot of effort into these batches. So you need a lot of manpower to actually abort them and correct them if necessary. And on the other side, even if you have these batches, there are still some kind of experiments that suffer from low robustness, meaning that for a very little change in the input data, you get vastly different outcomes. And if it's not properly documented which of these input parameters suffer from low robustness, you basically never know for sure if your experiments were reproducible. So let me just shortly clarify what I mean by reproducibility. So reproducibility is typically defined as a multi-stage process. In the ACM, we have a three-stage process. So first of all, we have the first step called repeatability. That means the same team can execute the same experiments using the same setup and recreates the same results. Reproducibility is achieved if a different team uses the same setup and comes to the same results. And finally, replicability is achieved if a different team uses their own setups and is able to recreate the original results. So we try to focus on a testbed-driven approach, meaning that we can only control our own setup. However, even if we control this own setup, we will be able to reach at least stage 2, meaning that we can, or we try to implement our testbed in a way that repeatability and reproducibility is achieved. And even for replicability, we can try to improve our documentation in a way that it will be easier for others to actually recreate the results. So how do we try to do that? So first of all, as I already explained, it's quite a lot of effort to make research reproducible. So what we first try to do is to reduce the amount of work that is necessary for others to reproduce the results. At the same time, we also want not to put too much effort ourselves into making experiments reproducible. So it should reduce the amount of works that is necessary for both sides. At the same time, we want to make reproducibility an integral part of the experiment design. So we don't need to do extra steps making our experiment reproducible, but it basically comes for free when we create our experiments. So they are inherently reproducible. And this we try to achieve by automating everything. So when I mean everything, I actually mean everything from the setup of an experiment, which needs to be automated, the actual execution of the experiment, and also the final evaluation. So everything from creating plots and evaluating results should also be part of the experiment. And the second problem, the low robustness, that we try also, or that we try to fix also. And therefore we need to document all the relevant parameters for an experiment. This we also try to achieve by automating the entire documentation of the experiment. And this should also not be an extra step, but be an integral part of our experiment design. And this we try to achieve by using a very well-structured experiment workflow. And this well-maintained structure then explains basically the entire experiment. Okay, so now how did we try to achieve these two goals? So we created our own testbed manager called the Plain Orchestrating Service, or short POS. So this POS is on the one side a testbed management system, and on the other side it's a well-defined experiment workflow. So if I'm talking of POS, I mean all the times both things. So if we now go over to how we actually achieve our two goals, so the repeatability, as I already explained, we achieved that by automating the entire experiment. If you have a look on the right, this is a very high-level overview over our testbed. We have a controller in the middle that actually controls the other experiment nodes, in this case, a load generator and the device under test. And if we now want to execute an experiment, we need to first load our images onto these two experiment nodes. And for all our experiments, we only use live images. Live images actually force the researchers to automate the entire configuration, because after restart, the entire configuration will be lost. So if the researcher knows upfront that only live images are available, he will for sure automate his configuration. And what is an additional benefit of such an infrastructure is that there will be no residual state between reboots. So we actually cannot forget a configuration step in one experiment, and this will influence another experiment, because we always start from a very clean slate. And by adhering to those both principles, we actually make our experiments repeatable. And to now achieve the stage 2, the reproducibility stage, we just need to provide access to other researchers to our experiment facility. And with a given access to our controller, the researchers can just re-execute the experiment and basically get the same results. So if we adhere to this kind of principles, our experiments become repeatable and reproducible at the same time. So let me just go quickly into the details of our POS methodology. On the right, you can again see our 3 machines. We have the controller in the middle, device under test, load gen as the experiment nodes. And every experiment starts in the setup phase, meaning that the controller manages the entire experiment. So we start our experiment script on the controller. And the first step, which will be performed, is the initialization of the experiment nodes. So first of all, we need to trigger a reboot on the device under test and the load generator. Then we need to push the live images or the Linux live images onto these 2 nodes via network boot. It's also possible to recover from any error states. So if the device under test was broken or misconfigured in a previous experiment, we can use specific interfaces to actually trigger a reboot on the device under test. We support several interfaces to trigger that reboot. The first interface would be the IPMI interface. This is an out-of-band management system that is typically integrated into big server machines. It's reasonably expensive, so only high or the bigger servers typically implement such kind of interface. However, there are also cheaper implementations. One of Intel's implementation is called Intel Management Engine. This is typically integrated into normal workstation PCs or even laptops sometimes. And we can also use this kind of interface to trigger the reboot. The big advantage of these 2 systems is that we can actually trigger the reboot even if the host machine is not reachable any longer, because these machines are not, or these 2 interfaces do not run on the host operating system, but have their own kind of controlled environment where they run. And finally, if none of these 2 interfaces are supported, we can also use a network controlled power plug, which basically means that we just switch off the power, switch the power back on, and this then triggers a reboot in the experiment node. And this allows us basically to recover from any error state in our experiments. So then after we have triggered the reboot, then started our machines, we can go over to the configuration of the experiment nodes. So one of the first steps in the configuration is to prepare the experiment. And this can be done by installing software on the experiment nodes or configuring of addresses that are necessary for the experiment. Then we also install some utility tools of our testbed, for instance, a tool that allows us to synchronize between 2 hosts. So for the later experiment phase, it will come in handy, for instance, if the 2 experiment nodes can wait on each other after certain steps have been prepared and only continue the experiment after these steps have been prepared. And therefore we use some kind of lightweight tool that allows us to communicate between the different experiment nodes via the controller. And finally, we also offer some kind of configuration possibility for our scripts. In this case, we offer global and local variables. The difference between them is that global variables are uniquely available for all different experiment nodes, and the local variables are only valid for a specific experiment node. And after we have then finished our configuration, we can then go over to the second phase of our experiment. This is the measurement phase. During the measurement phase, we perform the actual experiment. This usually or typically means that we have a repeated execution of a specific measurement script. So this measurement script is actually the script that generates some specific kind of traffic on the load generator, and on the device under test, often it is kind of a forwarding application that then simply forwards the traffic between its different interfaces. And during the repeated execution of the measurement script, we then use also different kinds of variables to configure each and every measurement run that we want to execute. For instance, what is often done by us is that we want to measure with different kinds of packet rates and different kinds of packet sizes during these experiments. So for each run of the experiment script, we typically use a different set of these loop variables to differ between these single experiments. I also put an example how it works on the lower left side of the slide. So in this case, we have two different kinds of variables, the packet rate and the packet sizes. So we want to measure with two different kinds of packet rates, 1000 and 5000 kilobit per second. And for the packet sizes, we want to measure with 64 byte-sized packets and 1500 byte-sized packets. If we now hand over these two variables to our experiment controller, it does some basic processing, meaning that we want to investigate each possible combination between these two variables. For instance, in the first measurement run, we measure with a packet rate of 1000, the packet size of 64. In the second one, we switch the packet size to 1500. And finally, in run 3, we switch the packet rate and then also the packet size and so on. Okay, and after we have then created our entire experiment, we can then simply run the experiment and collect the results. And the results are then finally evaluated in the evaluation phase. So the big advantage of using this repeated execution of measurement files and loop variables now allows us to associate each result that we created with a specific set of loop variables. And this is basically the metadata for this specific result file. And because our experiment now, or the controller now knows which result files were created with which set of metadata, we can then use this kind of information for our evaluation and our plotting tools. For instance, what is now possible is that we can aggregate over a specific kind of parameter. In this case, for instance, the packet rate, and then we can automatically aggregate over these kind of result files. And this then allows us to automatically evaluate everything, and we don't have to create a very specific kind of evaluation tool for each and every different experiment that we perform. The entire well-defined format for our POS scripts, the loop variables and results, then also simplifies the automated preparation of experiment artifacts. For instance, if you're interested in how an experiment looks like, we created a Git repository that is available publicly. Okay, so let me quickly summarize what POS is. On the one side, it's a testbed orchestration service, and on the other side, the experiment methodology that I just presented. The methodology makes experiments on the one side repeatable, because everything is automated, reproducible, because we can easily share access to POS with others, and finally, it makes it also easier for others to replicate the experiments because of our well-structured experiment workflow. So on the one side, POS reduces the effort to create reproducible experiments. And on the other side, POS complements the ACM awards. So these badges are still not obsolete, and you can still use them to incentivize the researchers, but our way would be an additional way to incentivize reproducible research, because we lower the effort for every researcher. So if you're interested in trying out POS for yourself, we created a VM with a lightweight registration process. We also created a repository that contains potential artifacts of our POS experiments, and also a website that describes experiments in more detail. So then, after I've explained to you the entire theoretical concept behind POS, I go now quickly over the actual features of our testbed that is also relevant for this event today. So what we typically use in our experiments is Ethernet. So we are typically using wired experiments with bandwidths between 10 gigabits and 100 gigabits per port that we want to investigate. We also optimize the entire testbed for low-level measurements, meaning that we typically prefer direct wiring between experiment nodes, because switches may introduce unwanted effects in our experiments, and then we cannot isolate the effects that were caused by the switches from the effects that we actually want to measure. We also created high precision and high accuracy traffic generation tools, for instance, the MoonGen packet generator. This uses off-the-shelf network cards, but in a way that allows us to precisely and accurately control the traffic patterns that we want to generate. So we can reliably generate constant bitrate and bursty traffic patterns if we want to. And we also can provide hardware timestamping in a very precise and accurate manner. What we also do for some experiments is the introduction of optical splitters. This allows us to passively observe every packet that is exchanged between our experiment nodes. And this allows us to also view the packet stream without any obstruction by the experiment system. And finally, we also do hardware timestamping in the nanosecond range with internetwork cards, up to 100 gigabits per second. So this is one of our experiments that is presented on the right. So this is a simple forwarder where we just measured the latency between every packet that was observed. And as you can see, each dot represents a single measurement in our test. So we use this to actually measure the ultra-reliable and low latency communication standard of 5G. And of course, for this very precise measurement, we need a highly accurate and also precise measurement facility. Our recent investigations I put also on the slide. So one of our papers was presented at HipNet and NOMS that contains similar measurements. And finally, what we also try to do is to make POS usable via slices. So what we can provide is low-level device benchmarking, isolated measurements for high-performance packet processing systems, this passive observation using optical splitters. We also have kind of more exotic hardware, for instance, P4 switches and smart NICs. And what we can also offer is GPS-assisted timestamping. So what we can offer is to make measurement facilities also available to other testbeds, for instance, via a combination of various testbeds to create distributed experiments. What we can also provide is an edge facility for other testbeds, in, for instance, a 5G context. And what we can also do is precisely timestamp the ingress and the egress traffic. So we're actually able to measure what we exchange with others. So thank you for listening. And I will now hand over back to the moderation.
Okay, thank you very much, Sebastian, for your talk. Let's move on to the next presentation, which will be given by Mandat International concerning the IoT Lab. Cédric, I hand over to you.
Yes, thank you. Hello, everybody. I will present you IoT Lab, what we offer in this testbed. You see my screen?
Yes, yes.
Go ahead. So IoT Lab is a testbed which is based in Geneva. The main experience from this testbed expertise, in fact, and working areas is Internet of Things and data protection. Though the goal of the testbed is to provide some services dedicated to the research. The final goal of IoT Lab is to exploit the results from the research to the industry. Typically, we can do some experimentation dedicated to Internet of Things in IoT Lab, and then to transfer the result to the industry. Typically, what we do, we have an approach based on ecosystem. So we are trying to solve all the problems linked to IoT. This means also security, data protection. And we serve also as an interface between the research, the industry, the standardization, and SDGs. As you know, standardization is an important point in Geneva, where IoT Lab is based, because you have ITUT and ISO, which are based in Geneva, and we have also the United Nations, and we are working together with SDG, the Sustainable Development Goals. So we have a direct liaison with ITUT. We are working together to do some standardization work, and we have also a lot of contact, in fact, with key academic institution and IoT community. Typically, we are involved with IoT Forum and IoT Week, which is an important actor in IoT in Europe and also worldwide. And we have a strong background on research activities. We have involved since more 10 years in European projects on IoT. The main expertise we have in IoT Lab is this research lab. So we are trying to develop new product or new solution and test these solutions related to IoT. We are offering the testbed as a service, which is a part of Slices, will be a part of Slices. And we are specialized in IoT, in particular in interoperability, multi-protocol integration, and certification. We are doing some certifications on IPv6, and we are also providing and working with the Universal Device Gateway as a service, which is a multi-protocol gateway for Internet of Things. The IoT Lab testbed is basically based on crowdsourcing and crowdsensing. Basically, we are collecting inputs from the crowd in general through different means. We're offering different types of resources, typically IoT sensors and actuators. We have also the possibility to use sensors installed on smartphones via an application, a mobile application. And we are offering also a LAMP survey server to produce and generate surveys related to IoT in general, but in the large scope, in the sense we can do surveys about use cases typically. And we have here the IP, the domain name of the IoT Lab testbed. Furthermore, the IoT Lab testbed has different elements. Basically, on the bottom, you have different sensors, IoT sensors, which are distributed on different locations, which is the base of the IoT facilities. And then we have IoT Lab cloud with different virtual machines on different servers to collect data from IoT sensor and to realize different experiments. And then we have the access to the different users of IoT Lab, so mainly the researchers, but also the crowd, which can use IoT Lab to provide some inputs. Then we are integrated since 3 years with Fed4Fire Plus Testbed Federation, which is the largest federation of next generation internet. The IoT Lab testbed is so accessible through the GFED tool and the Fed4Fire Plus portal. We are working also with TM Forum. We have a lot of work done through Iot Lab and TM Forum, notably to use the TM Forum Open APIs, because it is an important topic for the telecom operators. So we are trying to develop new solutions based on these open APIs and to implement and integrate specific use cases. Basically, we are trying to meet the most important requirements coming from the industry to realize these solutions based on TM Forum open APIs. We have several success also with TM Forum Catalyst, which is proof of concept, mixing research and also an industrial exploitation. What I have said previously, the Iot Lab testbed are used to develop, test, and exploit new IoT open APIs for TM Forum. Basically, it's a suite of open APIs for IoT device, IoT device, and also IoT service. Both suites of open APIs were developed in Iot Lab and tested in the testbed. Furthermore, we have participated in different TM Forum catalysts, so it's a proof of concepts. So we have several awards since 2 years, 3 years. It's based on different requirements from the industry, also different stakeholders and partners involved in the catalyst. The main idea is to realize proof of concept based on open APIs and other software provided by TM Forum, and to realize use cases based on the demand from the telecom operators. So we are very focused to the industry. Iot Lab is also a representative from FireWare. We are hosting a FireWare IOPS for Switzerland. So we are an official center for FireWare platform. So in this sense, we are exploiting the FireWare software and different components and provide this FireWare solution to the industry. So we are doing a requirement analysis, architecture design, deployment plan and support, integration, test and validation, and also capacity building by providing some learning courses. We are also involved with the standardization, particularly with ITUT. We are participating in different study groups, typically the study group 11, on signaling requirements, protocols, test specification, and combating counterfeit products. In this context, we have last year published a recommendation based on Fed for Fire Plus API of to handle the testbed federation. The recommendation is the recommendation Q4068 on open application program interfaces for interoperable testbed federations, which is very useful to federate the different testbeds. And we have also involved in the Internet of Things study group, SG20, which is focused on IoT in general for smart cities and communities. And based on the results and outcomes of the recommendation I mentioned before, we have created, we have participated, in fact, to the creation of a focus group on testbed federation at ITUT also, and we are chairing a working group on this activity on testbed as a service. We are also involved on privacy and security, so we are doing a lot of work to ensure the compliance to the General Data Protection Regulation, including data protection impact assessment. We have also developed different products and solutions to ensure the compliance with the privacy and data protection regulations. So typically the cybersecurity systemic assessment of risk and also the dynamic security and privacy seal. And we are working together to the Euro privacy certification to ensure the certification of products in compliance with privacy regulation, and also with ISO standard related to the data protection and security. We can contact us, Anna Brékine or myself, and also through the iotlab.com website. Thank you very much.
Okay, thank you, Cédric, for your presentation. And now let's continue with Sorbonne University, with the OneLab, the cloud infrastructure for researchers. Albert, the floor is yours.
Can you see my screens?
Yes, yes, we can.
Okay. Okay, so I'm Albert from Sorbonne, and this will be a relatively short presentation about the OneLab cloud research infrastructure. The facility is located in the campus of Sorbonne University at Paris. We provide bare metal cloud compute and storage resource to run cloud-based experiments. The infrastructure is composed of two different components. The first one is the Cloud Lab Paris cluster. It's a result of a collaboration with an innovative Cloud Lab project, US project, and it allows the researchers to build their own cloud software stack and to deploy it and test it. It provides the controls over compute, storage, and network resource and visibility all the way down to the bare metals. With OneLab credentials, it is possible to access all Cloud Labs site infrastructure, including the one that is in the US. Next is the hardware that we have deployed for this cluster. It's a H3 Moonshot. It's a 4.3U chassis with 45 ARM servers and 2 network switches embedded inside the same chassis. And the second component of the cloud infrastructure will be about the automation of a OpenStack cloud. With this, we have implemented some features to automate provisioning and configuration of virtual servers on the OpenStack cloud. It provides researchers with customizable virtual servers, such as customizable number of CPUs, RAM, and storage. It is composed of 3 controller nodes and 9 compute nodes, and provides over hundreds of compute cores to experimenters. All the controller nodes and compute nodes are interconnected with a 10 gigabyte SFP plus network switch. These are the hardware of the controllers and compute nodes are mostly Dell servers, and there's also some old Supermicro servers. For the accessibility, the resources are reservable and configurable in our portal. There's an additional options to automate the resource configuration with Ansible support. and also the bash script also. It's asked for a GitHub link, and then it will fetch the Ansible playbooks or bash scripts and run it automatically on the virtual servers. Once reserved, the resources are accessible via SSH directly if a public IP is requested for the servers or via a gateway. Our platform is mostly used by the PhD and researchers at Sorbonne University, and we also provide support for other projects such as we have deployed Kubernetes clusters and for other projects using our infrastructure. And this will be my presentation.
Okay, Albert, thank you very much. So let's continue with the University of Messina, the Stack for Things framework for Cloud IoT integration in an industrial environment. Antonio, the floor is yours.
Okay. Can you hear me? Yes?
Yes, very well.
Okay, thank you. So this is the title of the presentation, where I will try to present the Stack for Things environment with specific application to industrial systems. Okay, so I will start from some general consideration that are driving our thoughts and our development in the scientific field, where we are fully convinced that when you study a system, you have to consider the interaction and the consequence that this system will produce on the environment. So we decide to use open source, open hardware to share the data. These are other principles that are the basis of the way in which we proceed. And this is coming into a sort of methodology that we define self-conscious systems. The difference with the traditional approach in defining a system is that in the traditional approach, the system is considered done when you have solved the functional aspects and you provide a given service. But this approach that evolves through some different phases, requirement, design, construction, testing, is in some sense limited, is not resilient and neither proactive. There are some examples in different sectors. For example, in infrastructure, you build the bridge or the tunnel or the building and the project is over. But then there is an important phase where you have to understand how the environment is impacting or influencing your system. Similar things you have on the policy, when, for example, you have to keep the budget and you close the hospitals, but this creates problems on the population. And also typically on industrial site that were usually organized in such a way that you have to maintain the safety of the industrial plant, but the consequences on the environment are not always adequately considered. So this comes to what we call neurobiologic approach that is somehow inspired to the way in which our brain works. So we have the right part that somehow interact with the environment, collects the data, takes immediate decision, and is influenced by the real-time situation. The left side of our brain instead collects this data and learn, it stores the information, is able to predict and understand based on the experience on some strategic choice that has to be taken. This approach came in cooperation with a company that is named SmartMe.io to the production of some boards that includes the microprocessor, the microcontroller that represents the left and the right side of our brain, and the communication between these two worlds. So these industrial devices are able to collect data from lots of sensors, interact also with the actuators, but they also provide some interesting computational capability that makes this board a Linux machine. So it is possible to collect with the microcontroller the data and process have some logic directly implemented on board. And this open to the concept of edge computing. So these are the elements. And what we are developing step by step is a sort of stack where we have the edge device. We use this Arancino OS operating system for these devices. We use Cloud Stack and the Stack for Things extension that I will introduce soon, because we collect data and we have data management. We show this data through dashboard, and we can also implement machine learning. As you see, there are different technology there that can be used one or the other depending on the specific needs. Now we have the SLICE project. The SLICE project has been well explained by Serge, and it's important to have this system as an integration. An integration of research infrastructure where we want to share some common principle, API, mechanism to have experiments executed on this federated environment. So I want to focus at this point on a research infrastructure that interacts and works in the IoT world. What we want to develop is something that can consider the plethora of IoT device sensors and actuators so that are distributed all around, and create infrastructure that includes also these sensors and actuators. The traditional approach that we have in this area is related to this sort of figure where the IoT world is completely separated from the cloud environment. We collect the data and there is a latency there that we have to consider. We transfer everything into the cloud to take a decision and then back on the IoT world. In some cases, you can partially interact with the device if some API are provided, but usually these are proprietary solutions. What we want to do is to bring the IoT world inside the cloud, so the devices are part of our infrastructure, and they are to be considered together with the computing, the storage, and the networking facility that our infrastructure provides. This means that at the end, we want to have infrastructure made by some cloud part where we have virtualization, a virtual machine, but we also have the IoT world, the physical world, that can be integrated using similar principle and virtualization, creating one single environment where I use some device distributed somewhere, some others belonging to other users, connected with the virtual machine and applying virtual networking principle. Okay, so this is what we want to do. If this is possible, we can talk of software-defined industrial site, where the real environment, the IoT world, the physical environment can be sensed and controlled by boards like the one I showed before that collect data and transfer into the cloud. These boards are also able to implement edge computing. If necessary, they move into the cloud and they create an infrastructure that put together all these components. These are some of the technology that can be used for doing that. We started from OpenStack, that is a powerful framework to create infrastructure combining compute, networking, and storage element. And we added a fourth pillar that we call Stack for Things that represents the IoT components. Because as I mentioned, IoT for us has to be considered at the same level of the computational networking and storage element. This is an official project of OpenStack. There is the repository I indicated before. What are the basic principles that we are using? Are the following. So we have the IoT with the boards that are composed of processing and control unit, and there is some software running there that is named Lightning Rod. Then we have the cloud side with the Iotronic components, and these elements interact through channel, and we use WebSocket, so everything works at the HTTP level. It means that we can go through NAT and firewall without any limitation. And this is open to lots of real applications that can be done. The way in which we integrated this work inside the OpenStack is using absolutely the same philosophy. So we have a new service that is the Iotronic service, that is an extra service to the one officially offered by OpenStack, and it is able to create a communication channel with our IoT world. And we also separate the data channel from the control channel according to some very known principle. We use the bump protocol for doing that, and a sort of reverse channeling approach in such a way that each device becomes a sort of server, web server connected in the internet that provides services such as data from many different kinds of sensors. This is the way in which the OpenStack has been extended, modified with the new bump agent, Iotronic service, and the interaction between the different components. And this is what happened on the board, where we have the Lightning Rod software running there, and the virtualization of all the resources that can be provided by the board through many different kinds of sensors. This is the way in which we can integrate, federate, combine IoT environment belonging to different providers, and also how we can define access rules depending on who you are, what you're using, and what you can do with a specific resource. This is the way in which we implement the so-named service forwarding. So we have the cloud side, where you have a TCP server, and there is a public address that the external user see, but then the requests to this entity are automatically redirected through different channels to the boards, where there are counterparts that provide and interact with the specific sensors and actuators connected to that board. Okay, we can inject code, we can specialize the board and control the behavior with powerful capabilities, and we can implement networking, we can virtualize the networking. So we move from the physical network going up to the logical network, where we select the different sensors belonging to different physical network, but that are logically connected to one single network. It is part of my infrastructure. So I can integrate and combine resources coming from different providers. Okay, and this is extremely powerful and important in a smart city environment, as well as in an industrial environment. These are just some more details on how it works. I will not go too much on this. There are papers and that explain how this works. These are real examples of what can be done. In this case, for example, I have boards that are grouped, okay, creating different logical network. So boards belonging to the same user, for example, are organized to create a dedicated infrastructure where a specific service can be deployed. In the second use case, as you see, I have device separated and in the internet, and I can pick elements belonging to network 1 and integrate with the device on network 2, and I can group in different virtual network to deploy some dedicated service. Use case 3 combine the resource distributed in the internet with virtual resource on the cloud. So my infrastructure is made of virtual machine, of virtual storage on the cloud, plus virtual devices that are grouped together, okay, and belonging to different physical networks. The fourth use case extends even more and includes also mobile devices that are very popular, and so we have to consider also this possibility. This is the more complex things that is possible to do. We also open to the exploiting the edge capabilities, so to use this remote device to provide services. And by exploiting the chilling service and the Zoom service provided by OpenStack, we have the capacity to create containers, so virtualization, and also to use a serverless approach. This means that we can have a small function that can be distributed in our infrastructure and adopt the function as a service model to construct new service. This is a slide that tries to summarize how it works. The little functions are entered in the system through shilling, are distributed on the different physical device where they can be executed. And using Node-RED, I can define my flow in a logical way so that the service comes from the integration and composition of these distributed functionalities. This comes to the Web of Things that we are currently implementing, and I try to explain through this figure what is already available. We can expose services provided by our IoT device inside our infrastructure, using a sort of DNS mechanism that combine public DNS with dedicated DNS inside the infrastructure. It means that, like in this case, the service wt.rasp.univ.iot feluca EU is the address of the service. To solve this address, we use the DNS, and we are able to solve the first part, the public part, the feluca.eu. Then automatically it redirects through a service of DNS inside our infrastructure that try to solve the remaining part. So in this case, the Rasp Univ IoT is redirected through this NGX proxy server, and there is a sort of forwarding and translation of port address so that it enters this new server, and then the final part is also solved so that the WOT service is accessible. This opens to the possibility to have service dynamically created and mixing private and public address. So in this case, the board is offering a service like provide me the humidity, the temperature, and everything, and it can be immediately recognized at the global level. Okay, so this is extremely powerful. I can give you just this little example. I am using a normal and generic browser. This is the example that we are. And this is a board. We are only using HTTP. I am in Catania. This thing is in another city, in Messina. And I am only using HTTP. And I am controlling these objects. So I can switch on and switch off LED. I am controlling this. And only use HTTP. There is nothing else in the middle, using the WAN protocol and this way of organizing the DNS, we are assessing this service. Okay, I just go back and move toward the conclusion. Where is the presentation? This I can close, sorry. This? Okay, so Web of Things is these worlds where we are all these little services easily accessible through my research infrastructure. And to conclude, this is just the portal where you have a fleet of devices. For each of them, you have information related on the data that they are able to provide, and also on the internal behavior of the device. Okay, so to understand how the system is integrated in the environment, how it can impact and have a full evaluation of our system. Application on these things are with some companies in the trailers environment, where this big truck of 18 meters length are fully controlled while they are on the highway in Europe. We collect all the data of how these things is working, and we can interact with the device remotely and in real time. These are other applications on the medical fields where there is remote patients monitoring using the same sort of infrastructure. In this case, we are interacting with companies that provide this pole. We provide the internal components, and this pole is a sort of station where you can have Wi-Fi, LoRa, you have sensors, you have the lights, and many other services in one single pole, also like the recharging with regard electrical mobility. In this example, the infrastructure that I am providing is monitoring something like 12,000 different sensors installed in some part of the Italian highways. These sensors are accelerometers and inclinometers, and we provide real-time monitoring, collecting this data, having also some edge computation on board, and then they are analyzed to understand the status of the physical infrastructure in this case. Here there are some machines for food industry that are remotely controlled and monitored with this approach. This is a production of COVID masks that is totally remotely monitored and integrated in this sort of infrastructure. This is Prato La Serra, is one of the industrial sites of Stellantis and Ferrari, and we are providing some monitoring of some parts of this device to implement some preventive maintenance mechanisms. So sensors and boards that implement logic, they are all integrated, and this helps in the management of the plant in terms also of security and safety. Okay. Thank you very much. These are some of the links, and if there are questions, of course, I will be happy to answer.
Okay, thank you, Antonio. Let's continue now. The next presentation is from COSMOTE. And I will share my screen. Okay. So the Leonardo Lab is one experimental facility hosted in COSMOTE, which has the aim to foster research, innovation, and collaborations. It consists of 4 interrelated domains. We have an ICT cloud, a 4G, 5G non-standalone testbed, an IoT testbed, and a fiber to the home testbed. We have interconnections with research institutes in Greece, with NCSR Demokritos and the National Technical University of Athens. First of all, the ICT cloud comes in 2 versions. Comes in a vanilla OpenStack and Red Hat OpenStack. The vanilla one is based on Ubuntu server, It has more than 750 CPU cores, 1700 gigabyte RAM, and more than 150 terabyte storage. It uses open source tools like Prometheus, Grafana, and InfluxDB. And it has open source MANO and NFV deployments. It is integrated with the mobile network of our lab and is interconnected, as we have seen, with NCSR Democritus and NTUA. It is currently utilized by European projects like 5Genesis, 5G Complete, Interconnect, and more. The Red Hat Openstack is a testbed which has enterprise level support. It is aligned with the OT group. OT group is the mother company of COSMOTE and a member of the Deutsche Telekom group. This OpenStack is composed of 10 nodes, 3 compute, 3 controllers, 3 storage, and 1 director. It supports Red Hat Ceph storage and Red Hat Ansible automation. It is accessible to certified and validated partner SDN plugins and provides multi-tenancy access. The next testbed is the 5G non-standalone testbed. This is a lightweight Ethernet 5G non-standalone EPC core. We have also a MEC implementation via SGW local breakout, also from Ethernet. There is also an edge cloud hosting application and 2 Nokia AirScale base stations, which support 454 MIMO at 100 megahertz bandwidth. There are also 8 Nokia 4G Wi-Fi FlexiZone multiband indoor Pico BTSs. And these equipments are deployed mainly in the OT Academy premises, but also are distributed in the National Technical University of Athens and in the Democritus Research Center. This network operates as a private one using its own SIM cards, USIMs, and which are different than the commercial network ones. Regarding the 5G testbed, it is provides connectivity for specific demo sites, depending on the needs of the different European projects. For example, for 5G drones, we have provided 5G command and control for drone connectivity. In 5G force, we have been performing reference testing and application. For 5G Genesis, for KPI validation. It also supports system platforms integration, interoperability, and testing activities, mainly in 5Genesis, 5G Force, Unicorn, 5G Complete, Evolve 5G, and other European projects. The 5G standalone testbed is at the present time ongoing. It is going to be completed within the year. It also comes from Ethernet regarding the core network, including 2 user plane functions to emulate edge and core 5G network data planes. You have also control plane network functions like AMF, SMF, AUCF, UDM, N1, N2, N3, N4, and N6 interfaces hosted by the cloud infrastructure, and also supports network slicing, again, via the multi-tenancy access of cloud. Regarding the RAM, in this case, we have Ericsson baseband and radio. We use BBU 6630 for the baseband and radio units 4408 and indoor units IRU 8844
48 and small cells .4479. Regarding our IoT testbed, this is a testbed that has been developed exclusively by COSMOTE. It is flexible, scalable, and access and vendor agnostic. It consists of custom and commercial and services sensors like relays, power meters, smart plugs, air quality and temperature, humidity, pressure, etc. It consists also from IoT hubs and gateways supporting multiple access technologies like Wi-Fi, Z-Wave, Zigbee, LoRaWAN. It also comes with a common backend for data storage, processing and visualization, including MQTT, InfluxDB, Grafana, and Capacitor. And it also has Docker deployments and remote configuration device management. It is utilized in many EU-funded projects also. For example, in Interconnect project, it is used for energy management, home comfort, and security-related applications. It has been installed in 20 houses for this purpose. In Safe Crossing project, it is used for wildlife monitoring, automated storage, processing of cameras, videos, artificial intelligence, deep learning, visualization. For example, it is used in 45 underpasses along the Egnatia Odos highway in northern Greece. Also, it is used internally at the OTE group for energy management, automation, and physical security at telco sites. Regarding our fiber to the home testbed, it is also scalable. It can be used as a testbed for physical layer components and services implementation. It supports all network topologies, core, mesh, ring, access networks, and also network services, access, metro, MPLS, and Ethernet. Security applications can also be tested, and data encryption and physical layer cryptography components. It also, in conjunction with the R&D data center and the 5G network, can combine different technologies through access network. For 2022, we have planned to integrate commercial QKD appliances, advanced encryption, and integration with IoT. The lab interconnection is, as we said, with NCSRD and NTUA mainly, but we also have an interconnection with an Ericsson EPC, which is deployed in the Greek-Turkish corridor in the context of 5G MOBIX project. Now this is connected with an ENM from Ericsson, again, deployed at COSMOTE's lab testbed. Our lab is part of the 5G Genesis, a European experimental platform, and is part of the pan-European experimental platform 5G MOBIX. Regarding the telco sites, we have also developed internal applications, solutions, and tools. This can be used for power energy monitoring regarding AC and DC currents, for energy management, for remote management of any Modbus enabled mode element, for air conditioning, remote control, for temperature, humidity, air quality monitoring, and there are also service and there are also available sensors for fire, flood, door, window, door status, etc. Also, it provides end-to-end physical security, being able to detect any object using artificial intelligence, combined with PIR and microwave activity detectors. Also can provide object tracking, alerting, visualization, and visual and audio alerts. It supports any wired and wireless camera from any vendor, both commercial and custom indoor and outdoor ones. It also provides access control, face recognition, door lock and unlock, antenna and microwave dish tilt alerting powered by 48 volts battery. Also voltage monitoring using a narrowband IoT module for micro base station site alerting. Now regarding our lab access and potential uses, the Leonardo infrastructure is used by more than 25 European funded projects. Its main use is, of course, for hosting demos and trials. More particularly, the Leonardo Cloud can be accessible from anywhere via VPN connections. It is used for services, applications deployment, and for hosting management related software. Also, the 5G testbed, the non-standalone and the standalone one, can provide coverage for the OT Academy premises. Other locations can also be covered. However, this particular testbed cannot be shared or accessed remotely. The Leonardo IoT testbed is accessible from anywhere. That means that any sensor can be integrated through a common API, while data monitoring, visualization, alerting, and data retrieval are also available. And finally, our fiber to the home testbed can be accessed locally for a variety of physical network services, implementations, and security applications. That's all from my side. If there are any questions, I will be happy to answer now, or if you have questions that you can think of later, you can send me an email and I will get back to you. Okay, so the next presentation comes from Poznan Supercomputing and Networking Center, the author of the Polish node for industry and SMEs. I will hand over now to Bartek. Bartek, the floor is yours.
Hello. Thank you, Kostas, for the invitation. And can you hear me and can you see my slides?
Yes, very well, thank you.
Okay, thank you. I would like to present our offer for the industry and SMEs from the Polish side of Slices. So basically, our node is based on projects from National Roadmap of Research Infrastructures. There are 3 projects. I will go very briefly through all of them. I would like to mention that all these projects are currently in progress. So we expect this infrastructure will be operational from January 2024. So in the first open call, we share limited resources only, and the details are available on the website. So instead, I will focus on, in this presentation, on our plans and how we plan to share the infrastructure, what kind of services this infrastructure will offer. So the first project, this is our flagship project. The biggest project we have is a Pioneer Lab, the national platform for integration of research infrastructures for innovation ecosystems. So this infrastructure is built by 21 partners, interconnected by Pioneer network. So all the nodes of the Pioneer Lab are interconnected with at least 100G connectivity. In several locations, you have multiple 100G connections between laboratories. We plan to deploy 8 laboratories, which are totally distributed around Poland, but they are interconnected and interworking. So you can imagine all these laboratories as a single laboratory, so you can access different resources from different locations, and moreover you can access different resources from different laboratories. So at the end you compose quite a complex environment for your research. I will go very briefly through the laboratories we offer. Instead of reading and providing the details of the laboratory, because I need to explain, explaining each laboratory may take an hour or so. So I just would like you to remember keywords which are behind these laboratories. So the first laboratory is focused on networking. It's a laboratory of innovative network technologies. So it's based on our fiber routes we own in Poland. It covers optical and packet domain. And basically this environment provides virtual networks for industrial and scientific research. The second laboratory, a distributed laboratory of time and frequency. So here we offer a distributed, based on dark fiber infrastructure, laboratory for synchronization of time and distribution, time and frequencies signals from atomic clocks. We have regional time and frequency repositories, level 1, level 2. So depending on capabilities of atomic clocks, we have the different architecture, and we distribute the signals to our potential customers. The third laboratory, Smart Campus as a smart city laboratory. Here we talk about smart campuses, all the Internet of Things architectures. This is implemented by 13 scientific centers in Poland. Energy saving solutions, platforms for interoperability between different IoT systems is in focus of this laboratory. The fourth laboratory, Living Labs, regional living innovation laboratories inspired by ICT. It's for different sectors. It's for students and teachers. It's for a science sector and for a business sector. So it's a typical living lab laboratory where you can meet all the people. It's mostly for startups, so we can meet people, have creative ideas, and build solutions, technical solutions. The fifth and sixth laboratories are concentrated on computing. The fifth laboratory is a cloud computing laboratory. And actually this is focused on unexplored market segments. So on scaling resources for clients from 1 to 1,000 CPU. And this is not actually covered on the market at this moment. And building new cloud architectures adopted to large-scale applications. On the other hand, the multi-scale laboratory, it's a different laboratory where we provide skills and personnel which can help people to translate their own big computing tasks into multi-scale tasks, so we can run your applications in more efficient way in the big computing infrastructure. The next laboratory, e-training. Laboratory and e-training services. It provides a platform where customers can create their own e-training sessions, materials, but also this laboratory concentrates on providing e-training materials for Pioneer Lab as a whole. So this will be a source of information for potential customers, how to use other laboratories and what are the technical specifications of other laboratories. And the last laboratory, pre-incubation. This laboratory is concentrated on soft activities. It's not a technical laboratory. Instead, it provides expert consultations, legal, economic, and technical, how to create business, make business out of the technical work you can do in Pioneer Lab. So the outcome of this laboratory might be a business plan or a new ideas for startup companies based on research done in the project. So this is the first project. The second project I would like to present today is 5G Lab Polska, a national laboratory for advanced 5G research. So in this project, we built 3 distributed laboratories in 5 locations. We have 6 partners that are listed below. So we have 5G network laboratory, a laboratory of simulators and measurement tools, and 5G environment laboratory. As you can see on the map, all these laboratories are interconnected with Pioneer network, again, 100G interfaces, and all of them work tightly together. So few words about 5G network laboratory. So we concentrate on 2 aspects. On one hand, we create multi-regional standalone operational network, 6 locations, 6 partners in Poland. So the goal of this multi-regional 5G network is to provide a stable operational environment for testing new applications and services in the network. And on the other hand, we have also local RAN installations, and these are typically for more disruptive experiments, different locations, different potential applications, from airport facility to Baltic Sea or partners' headquarters. So mostly all the experiments regarding Open RAN or any disruptive experiments which will not affect the multi-regional operational network. The next laboratory is for simulators and measurement tools. This is basically support a service for other laboratories, so we can create more complex research environments and provide it with tools to monitor your environment, or more importantly, simulate, if needed, user equipment or elements of the 5G core 5G core system in your network. And the last laboratory in 5G Lab Polska, 5G Environment Laboratory, and this laboratory is concentrated on applications. So how to make use of the 5G or 6G in near future infrastructure, how to develop new applications which are useful for community. These are just examples: multimedia, airspace industry, e-health, maritime industry, energy, industry 4.0. These are the examples. We are for sure, we have expertise to bring new novel ideas in the field, but we expect more coming from our potential customers. And the last project I would like to present, and the offer from this project, is the National Laboratory for Photonics and Quantum Technologies. This is a big project, but I would like to concentrate on one part of it, just a laboratory of quantum cryptographic key distribution. So in this project, we built a link, long-range link between Warsaw and Poznań. It's a trusted node QKD link. We have local links in cities in Poznań and Warsaw. We integrated, or we plan to integrate existing optical data transmission systems with QKD systems, and we would like to have some research on as an optical carrier of time and frequency signals from atomic clocks. So we would like to mix the 2 areas, QKD and atomic clocks, precision time systems, to make new applications. What we have available currently, as explained, all the work is in progress, so we are still in the design and implementation phase. At this moment, we have installed encryptors in our facilities, R&D laboratory, the QKD laboratory equipment, the random generators, quantum random number generators, and the production systems, all of them from ID Quantic. This is just a quick overview of our local QKD testbed in Poznań. it's based on our operational network. So we share this infrastructure with the laboratory. We have several links installed in our city. We work on the ambitious use cases. One of them is a QKD cross-border connection. Another is reference, as mentioned earlier, reference time and frequency use case, which involves long-distance connectivity. At this moment, we are investigating how to apply SDN solutions for QKD. So regarding quantum communication, we welcome representatives of industry for cooperation in the areas I mentioned on the slide. But I must admit, it's a bit more complex than a traditional computing on networking experiments, because it requires the presence of the personnel on site, because mostly all these technologies are available only on site, not remote access is not possible. Just to summarize and conclude, we are aware that these laboratories are in the construction now, but we invite industry representatives to the discussion and potential use of the research infrastructure and future research projects. So the scope of these laboratories is quite high, broad, but we specifically would like to highlight some areas we gain expertise and we can cooperate. So it's optical networking, quantum communication, 5G technologies, and 5G ready applications, and edge and cloud technologies. Thank you very much.
Okay, thank you, Bartek, for your presentation. Now let's move on to University of Thessaly. Nikos is going to present us the Iot Testbed, an integrated facility for beyond 5G research. Nikos, the floor is yours.
Thank you, Costa. Yes, you can see my screen, my slides.
Yes, yes, we can. If
okay.
you can put it in, you can enlarge it, put it in.
Maybe now it's better?
Yes, yes, now it's better. Thank you.
Okay, so hello to everyone. My name is Nikos Makris, and I am a postdoctoral researcher with the Department of Electrical and Computer Engineering, University of Thessaly. So a few words on who we are. Our university is a relatively new higher education institute in Greece. It is located in the city of Volos, and our lab is the Network Implementation Testbed Laboratory, directed by Professor Thanasis Korakis. Over the years, we have been participating in different research activities in the field of wired and wireless networking, cloud computing, and smart cities. The overall goals of the research team in University of Thessaly is experimentally driven research with different, mainly wireless, but also wired, programmable wired communication networks as well. We also have some activities on cloud and edge computing, mainly on the virtualization of the networking components that are hosted at the cloud or the edge. And also on IoT with the development of new prototype platforms for wireless sensor networks that integrate different wireless communication technologies, like, for example, LoRaWAN or ZigBee or 802.11a8 for the communication. And on top of that, we apply machine learning techniques for optimizing the network operation. The key tool for this research is the Iot wireless testbed, which is a research experimental facility that supports the research activities of the lab in the EU level. Iot stands for Network Implementation Testbed using open source tools, and we support multiple wireless technologies for experimentation, like, for example, Wi-Fi, 4G, or 5G. We have programmable wired networks with OpenFlow, and SDN, NFV, and sensors, and things like that. The testbed has served as a key testbed facility for multiple European projects in the past, and we constantly upgrade the testbed with state-of-the-art hardware and software. Now the testbed is available to the research community in a 24/7 fashion, and it is designed in a manner so that it's able to achieve reproducible results in the experiments, while also operating in under real-world settings. Now, the testbed is provided to external users through either our own tools like the Nitos portal or other tools like, for example, the Slices SE portal, which is available for the first Slices SE open book. There also parallel experimentation from different users is possible in the testbed. By allocating specific isolated slices of the infrastructure to different users and not allowing them to interfere with each other. Now, the testbed is based on open source software that allows us to further expand the capabilities of the testbed and the provided functionalities by using the same hardware and just building things in software. Now, overall, the testbed is providing in total more than 100 wireless nodes. Now, these nodes are mainly high-end PCs equipped with Core i7 processors, 8 or 16 gigabytes of RAM and solid-state drives, and also multiple wireless interfaces for experimenting with Wi-Fi, 4G or 5G networks. We also host a private LTE network based on operator-grade commercial off-the-shelf hardware, and this is soon to be extended for 5G operation as well. We also host a citywide wireless sensor network, which is operating over the LoRaWAN technology and is able to achieve connectivity for up to 10 kilometers in line of sight conditions. We also have some millimeter wave devices that can be used for experimentation, supporting point-to-point and point-to-multipoint communication. And the experimenter can also steer the beams of the units with a step of 15 degrees at each time in order to allow new topologies using this millimeter wave mesh system that we have. In total, we are able to provide more than 20 USRP radios, software-defined radios that can be used with software like, for example, Open Air Interface in order to experiment with real radios. And these devices are mainly USRP B210s, but also some N300 series and X300 series are available for experimentation. And the entire testbed is having an open flow based experimental plane for the experimenters so that they can use their own open flow controllers in order to control the traffic that they generate from their experiments. This plane is soon to be extended to support P4 as well. We can also provide a few mobile nodes, but mainly what we can do is we can provide emulated mobility by using programmable attenuators, which are mounted at the antennas of some USRPs or the private LTE network. And through some mobility patterns that we have collected throughout the city, we are able to replicate them in the test. And all of these components are backed by a cloud infrastructure, which is used mainly for supporting the testbed operations, but some experimentation virtual machines can also be hosted there. Now, all this setup is basically deployed in 3 different locations, so we are able to offer an indoor RF isolated setup that has no external interference. We have an outdoor setup which is prone to external uncontrolled interference. So these are the most harsh settings if someone needs to develop a protocol that that should operate against the worst possible settings. And finally, an office setup with low external interference. And now resources from all these different setups can be from the different locations and from the different technologies can be mixed in an experimental setup so that the experimentation capabilities of the testbed are almost limitless. Now some pictures of the testbed. So for example, you can see here the private LTE setup with the programmable attenuators mounted. On top, the millimeter wave nodes, the cloud infrastructure to have, and the external testbed, the outdoor testbed setup. So all of these components allow us to experiment with emerging 5G and beyond technologies, like for example, open source 5G with software-defined radios, and mainly employing platforms like OpenAir Interface, with edge cloud deployments that can offer minimized latency. Antennas with these programmable attenuation patterns for emulating mobility in the testbed, and point-to-point millimeter wave units that are available with the beam steering capabilities in order to test scenarios for fixed wireless access. Now, over the past years, we have been implementing, validating, and offering different frameworks over the testbed.
Μια χαρά. Εσύ τι κάνεις? Καλά.
So as I was saying, over the past years, we have been implementing, validating, and offering different frameworks over the testbed. I will go through a few of them just in order to demonstrate the type of experiments that are available, that can be deployed in the testbed and possibly extended through, like for example, an open call process in slices as seen. So the first one is on a heterogeneous cloud implementation. So the cloud run is basically when we the part of we disaggregate the base station, and part of it is being executed as a network service in the cloud. So now this is this type of split has been standardized in the 5G new radio specifications. And now what we did is basically on this setup where we have the central unit communicating with the distributed unit, we have implemented the respective signaling for integrating non-3GPP access by means of a Wi-Fi network access to the network. So using this, we are able to augment the network capacity and provide multiple links to multi-homed UEs that participate in the network, and therefore the users can perceive better performance, like for example, when streaming UHD video over the network. So now following this, what we implemented a multi-access edge computing framework that is able to operate over this heterogeneous cloud run setup, with the overall goal to minimize latency for accessing services over the different heterogeneous networks. So we, given this setup, with the MEC architecture, the concept of the MEC architecture is to break out traffic at different locations, like for example, either at the backhaul network before the traffic is reaches the core network, or at the core network at the UPF component. So what we did is we developed the respective functionality in order to break out traffic directly from the front haul network, the network that is basically connecting the central unit and the different distributed units. And this is done by implementing a multi-access edge computing agent that is hosting these services directly reachable from the DUs of the network. And some results indicate that when using LTE or Wi-Fi, we can, in the test setup, we can bring down the latency to less than 10 milliseconds. Now, based on this setup, the next work is based on running this multi-access edge computing framework in a cloud-native setup. So we pack everything in Dockerized containers and instantiate the network in the testbed using the Kubernetes framework. And by actively monitoring the user delay that the user sends from the from the phone when accessing either the 3GPP or the non-3GPP DU and the communication with the MAC host, we're able to dynamically conclude on whether some SLAs that the client has contracted with the operator regarding the latency are preserved or not. And if they are about to be broken, then we take the decision to migrate in a live fashion the service from one MAC host to another. And finally, last work is based on artificial intelligence-driven network scaling. So the goal for this work is to actually rearrange the telecom network and make it to dynamically self-adapt and assign slices in real time, depending on the type of the applications that are running on top. So in order to do this, we are using again a cloud-native design for the network. And we monitor the traffic that's being exchanged from the UEs towards the different services in the internet. We monitor traffic at the core network side, and when we classify these types of traffic, and based on some models that we have trained our algorithms with, we conclude on the future allocation of resources. So, for example, if we see that the WebRTC client is about to send massively traffic in the network, we assign a high bandwidth slice for that at the LTDU side. And since the last work has also received the Reproducibility Award by being able to be deployed and the same results to be able to be captured from a different group using a similar setup like the one that we have been using. So now, before closing my presentation, a few words about our role in slices. So we bring in knowledge on how we can manage wireless devices in this testbed type of setup. So we bring in experience from lessons learned from operating the Iot Testbed for almost 15 years now, and on how the equipment should be managed and how users can be isolated from each other when running experiments in the wireless domain concurrently. And our overall goal is to continuously upgrade the testbed offering that we are providing through the Iot Testbed. So thank you all for your attention. If there are any questions, I will be more than happy to answer them.
Okay, thank you, Nico. Now let's continue with University Carlos III of Madrid with the 5-tonic lab presentation. Carmen, the floor is yours. We cannot hear you.
Can you hear me now?
Yes.
Okay. And the slides?
Yes, very well. Thank you.
Okay. Well, thank you, Kostas, for organizing this industry day. I'm going to introduce you 5-tonic. It's one of the facilities that we have been running for several years in Spain. And just to identify, in Spain, we have two nodes. One is hosted by India Networks in Madrid, and the other one is in the University of the Basque Country in the north of Spain, that my colleague Eduardo will introduce later. This is the two nodes currently established in Spain for the slices infrastructure, and what I am going to introduce now is that the ecosystem behind the 5-tonic infrastructure is not only a set of resources, technical equipment, human resources, training activities, but there is currently a background of several years of running with verticals, with SME, with different industry in Spain and in Europe mainly, different experiment that bring us the opportunity just to serve this infrastructure for the slices deployment in the coming years. This is the demo room of Phitonic. Here we can see where the main demo take place, and on the right we can see where is the data center, and this is basically hosted in India. And we can show different at the same time, or in the same room, we can show and have in parallel running different demo and different infrastructure for several projects. Here we can see, for example, some use case on smart urines. We can see the different deployment of the 5G. We can see also a specific use case from one project on gaming. This is a very dynamic room that we can change and use for the different experiments that take place and the different demo that could take place within the infrastructure. What's the main objectives of this infrastructure Phitonic? It's an open laboratory, mainly founded by Telefonica and India Network several years ago. And there are four main axes where this lab works. Basically, we made technology development through European projects, standardization activities. We also have joint venture and startup advanced training. We have some example of that training that I will show later. And we have multilateral trials with interoperability with different actors. We also have the option just to have pilot services to large verticals customer. And I will show some example of that verticals. And some of them have been running in some European projects, and other are the vertical that finally are coming by the hand of Telefonica or other companies, and they want to test the pre-commercial of the research or whatever level of maturity in the development that they have. And we also offer an access to an academic environment jointly used and India that is very rich also just to motivate the research challenges in this infrastructure. And there is also a place where there are demonstration of European projects. There are exchange of technology and joint action with different level of administration. This is a very rich ecosystem that we have been running and that we are changing, and that there are different challenges that we have to cover in the coming year just to evolve this infrastructure for a more mature facility for experimentation within the slices. The governance of Phitonic is an example that has been took in the past for an example of sustainability, because we have a core member. They fund the infrastructure. So to be member of Phitonic, you have to fund the infrastructure. You have to put resources economically and with devices, equipment, and human resources. The current Phitonic members are listed there, mainly the main two founders, co-founder Telefonica and India Network, but another important are Ericsson, University Charles III, Intel, Scope, Capgemini, and InterDigital. This is open to different industrial and members academia that want to join us. There are several agreements. There are several levels just to join us. And this is something that obviously it's a closed ecosystem, but it's open if you put the resources just to play together with us. There are collaborators. They are involved in specific Phitonic activities, but they don't have decision on the main evolving of the infrastructure, and they just participate using the shared infrastructure. They collaborate with projects, but they are not formally members. This is the governance that we have in the lab. The main activities are covered in 4 main aspects. We have technical activities just for evaluating use cases. There are technical activities for technical components, just to evaluate pre-commercial devices that some particular company has want to test. We have technical activity related with European project, and we have also dissemination and impact training activities. There are several examples on the right. For example, just to highlight some of them, in the case of the use cases, we have a very successful example of autonomous vehicles in industrial environment with HT robotics, that they have permanent equipment areas for deployment the application on that vehicles, and this is a demo that is very, very successful in our lab. We have also experience in the past and currently with emergency services in cooperation with the emergency services in Madrid City. And we have another example of augmented reality services in fairs for tourists, for example. And another example, for example, in the technical component, that it's a new technical solution, probably pre-commercial, that some company want to test. And we have some example, for example, the integration between the front hull or back hull with Ericsson and Telefonica that took place in our labs. A new high frequency signal generation, the technology with Wavelabs company. In the case of the European project, we are very proud that we have been running, for example, the 3 ICT 17 projects that basically the objective of that project was to create and interconnect different experimental facilities across Europe. That's 5G, Ipmi, and Genesis. They were infrastructure, and there were use cases running for in our site for these 3 projects. But there are all other projects, other European projects, that like the EXA, that is one of the flagship projects for 6G definition. And we also are involved within all the umbrella of the project of slices in the design and the supporting community. And in the next one, that is the preparation phase. And in the case of the dissemination activities, I just want to highlight, for example, a very important training activity that had been taking place since the last 6 years. This is a need from one company, Ericsson, that they want to train people on specific technologies. And jointly with UC3N, we created a very successful master on FDN and SDN in 5G network. And this is one example of one of the access on training activities that we are also very proud within Phitonic. Well, the working procedure in Phitonic, obviously there is now an open call. We are participating in that open call running by Slice JSC. But apart from that, there are a governance or a different step that we have to cover. Basically, there is a steering board that it's all the project trial experiment and all the equipment that we want to install there, they have to be approved by this governance body. And each trial, at least there should be one Phitonic member that may include other collaborators, but typically this is something that it's very easy. Yes, if you want to test your application with some particular equipment that is in place by one of the Phitonic members, is just establish a collaboration. Say, okay, I want to test my application with that infrastructure, and this is something that it's very open, but there is a minimum approval by the steering board. There are our plan resources, location, dissemination. There are resources, not only the infrastructure, but also the human resources that we have available just for running the experiment, for implementing and supporting the connectivity and so on. There are dedicated resources in the infrastructure, and there are shared resources in the infrastructure. Dedicated resources is just cover one specific trial and experiment, but there are also shared resources that any member of the infrastructure can use. And Phyton is also very involved in the academic activities jointly with its master and in collaboration with UC3N in different training activities. Considering the use cases, here we have on the right of the slide several examples of very successful vertical that have been playing with the infrastructure, and there are use cases with potential short-term commercial applications. So there are vertical that want to test some pre-commercial application, and they just want to play with infrastructure in our environment. The main strategy just for these vertical use cases is involving final users. For example, in the case of the emergency services, we play with the real emergency services in Madrid City, ensuring that the implementation is based on commercial and pre-commercial equipment rather than an experimental one. We have part of the infrastructure for experimental, but obviously we have also very, very close to the market devices just for the vertical to experiment. We emulate as much as possible the realistic operational condition, and we try to find synergy with other Phytonic activities. There are very close related projects. There are common participation between these vertical use cases that are across the different European projects, for example. Just to highlight some of the verticals, we have the emergency services, SAMUR. We have Fitur, that is the main show of for tourists in Spain. There are some banks, some retail, some automotive, some utilities, energy. All of them have been running vertical use cases in our infrastructure via European project, via close collaboration, via different ways. In the case of the technology trials, the objective of this trial is to develop and validate the main enabler that will make some particular, in that case, 5G in the past and 6G use cases, just to make this infrastructure feasible for techno-economical aspect. The main focus has been virtualization of the different network function, network slicing, integrated transport from backhaul and front haul, using high frequency bands and use the standalone core and the future development that is expected to have in the lab. It's not only pre-commercial, but the rusted technologies. We have a very competitive academic and research environment within India and UC3N. And there are different technologies that make sense just to test in our infrastructure. One example is about crypto, quantum cryptography network integrated in 6G, new antenna, new signal generation technology in optical processing. This is a summary of the European project that had the opportunity just to use Phytonic infrastructure in different way. Basically, just highlight the 3 ICT17 project and other Eurozone 2020 project where there has been a strong work on vertical use case demonstration, like for example 5G growth. Well, this is not very easy to see, but what I want to highlight here in these slides in the Phytonic infrastructure is that by one hand, there is one particular company with some devices in place in the infrastructure. Part of that could be shared or dedicated for a specific project. It's depending on the agreement between the different parties. There is also integration with Telefónica Spain lab. This infrastructure is not isolated. It's also interconnected with Telefónica Research Lab. There is a data center where the different projects host the resources. And one part that I want to highlight also is that this is very flexible. For example, we have here the 5G backpack. This is one 5G deployment that let us just to be portable and use in different locations just to demonstrate. If we want to go to the center of Madrid, we can go with that and make a specific trial or demo in that location. So this is something very complex, but at the same time, there are fixed infrastructure that cannot be moved, but there are the idea is just to have portable infrastructure that can be on demand and move and in different locations. Well, the main challenges of Python is for the future, for being part of slices. What we offer is that we have an international multidisciplinary ecosystem. There are a strong position of industry and lab, academia, government, and users. We have a very successful example of sustainability of that ecosystem, Python, and the practical experience in governance for models for research infrastructure. Building human resources in this infrastructure is a key aspect from local to global. We have training, high qualified staff, agreement with industry and university, and this is a very dynamic ecosystem just to move and support the human resources needs of slices. In the research perspective, we're defining the research agenda of this kind of facility, what is expected of these facilities in the coming 10 years. And this is something that we are also in a good position just to identify the main research topic of that facility. So in general, it's an academia research and innovation hub that has been very successful in the past year, and we expect to provide the enough resources just to successfully in slices in Spain and globally. That's all from my side. So in case any question, I will be happy to respond, or offline in case of more technical details about the equipment and the facility. Thank you.
Thank you, Carmen. Thank you for your presentation. The next one is from IMEC Ghent University. The presentation is regarding the Iot Testbed portfolio for networking, cloud, artificial intelligence, and IoT research. Brecht, the floor is yours.
Yes, thanks. Good afternoon, everyone. So I will tell something more about the testbeds we run at IMEC in Belgium. And more specifically, they are oriented towards networking, cloud, AI, and also IoT research. So let's start with, there's a documentation page. So if you want to look up anything or you want to create an account to use them, doc.ilabt.imec.be. So all the resources that I'm describing are actually real hardware that's remotely available for experimentation. So you can see some pictures already on the slides, but I will go into some more detail on those. So actually at IMEC, we do have a range of testbeds ranging from technology-driven testbeds. So that means certain technology, for instance, wireless or 5G or cloud, you want to do some research or some classes, well, then those testbeds are available for you. If you look more to the right side, these are more application-driven. For instance, to the right, what we see is a library in Ghent, in Belgium, which has actually some sensors available, which can be used for some applications. For instance, to look where free seats are available or where people are located. So that's a full range. I will focus today on the more left side of the labs for more technology-driven research. On top of that, what we also have is some more higher layer testbeds. So for instance, we do have servers with GPUs, but what we do is we have a testbed called GPU Lab, which abstracts more. So for instance, you do not have to install any drivers, any software. You can actually just start with a Jupyter notebook and have access to those. So that eases a bit, especially if you look to big data, to AI, to machine learning kind of research, you want to start off immediately with those. We also develop our own tools to access those testbeds. And we also have some specific hardware that has been developed in the past. So let's start with the virtual testbed. So that's actually a testbed with more than 500 bare metal servers available. You see some of them on the picture, and it's oriented fully remotely experimentable, of course. For instance, what you see is you deploy some clouds, you do some experimental networking in between, and you can actually do research on all those things. So how it works is we have a bunch of servers, and you can actually define the topology as you want. You see some examples in the pictures. So that is flexible. You can create multiple experiments, for instance, using some clients, some servers, maybe some network environment in between. And that is available for you. You can define that, you can run that. You can share even those experiments with multiple experimenters, so you can easily do whatever you want on those machines. An example of that is, for instance, OpenStack deployment. You have bare metal servers. There is some tool developed by Indra in France, which is called Enos, and that helps, for instance, to deploy a full OpenStack experiment or setup for your experiment. So that's, for instance, an easy way of experimentation. The same is true for Kubernetes. That's typically used for instance, scaling up experimentation. You want to have testing of a device under test, some scalability research, some performance research. You use, for instance, Docker containers to scale up your client side. That's also something that's easy to deploy there. If we go to the GPU Lab testbeds, so as I said before, more oriented towards machine learning AI, and actually there are 3 ways of accessing that testbed. So the first one, as you have seen before in the virtual, you can do a bare metal access to those servers and GPUs, but there you need to install all the libraries, the drivers, the software, but you have full flexibility, of course. But then comes 2 easy ways. The first one is Jupyter Notebook, so that's web-based. You can do easy examples of your experiments, and then typically the people for more larger data sets or longer running experiments, they use the client-based job system. So that means you see an example of such a description of a job. So you define the number of GPUs you want, the number of CPUs, RAM, etc. And then it is scheduled and it runs whenever resources are available. So that's very easy to do. Of course, multi-GPU jobs are also supported, so you can actually use multiple GPUs in a single job. What resources do we have? So there's a list here. So we have actually a range of GPUs up to the newest, such as an NVIDIA 8100. We have more than 125 of those cards, and our top systems are actually 2 AGX2 systems, which have 16 V100 NVIDIA cards in them, plus a large number of RAM. So that's available in the GPU Lab infrastructure, is shared, of course, but based on the job-based system. They will be, in short, that will be actually done over summer, interconnected by a 100 gigabit InfiniBand network, so that all of them have access to the fast NVMe storage. For now, only the AGX2 have that access. So that's something we want to extend to all the GPU nodes. Then we have also a wireless test bed. Actually, 2 locations here. So the first one is in a data center with 44 embedded PCs, which are actually on top of the racks. So quite a lot of metal, of course, in that room. And the second one is what you see on the right side, a more industrial room with 100 fixed nodes, 120 fixed nodes, but also a number of mobile robots. So you can actually do some mobility experiments, handover, for instance, in there. So you see also the floor plans of how the nodes are spread over the room. These are some more screenshots or pictures, actually. So for instance, on the top right, you see an example with more than 100 tablets, which wanted to do a multicast test based on the wireless, on the Wi-Fi, to see what happens. And you see also one of the mobile robots going in between those tablets. There's also a lot of software-defined radio available. Different flavors, also FPGA-based, so you can have a lot of experimentation. We have also developed an open Wi-Fi code base, so you can actually have a full stack of Wi-Fi running on those software-defined radios. So you can adapt that stack to do some experimentation there. Beyond that, we have also the IoT office lab. So now we're coming in IoT domain. So we have actually 3 floors of our building are equipped with IoT sensors. So let's see our remotes. These are together with embedded PCs. So also there you can actually do some experimentation in a real office environment. So that's some examples from of those devices. So the latest are the Solercia remote. We have added our own ultra wideband shield, so also that can be used, of course, for some experimentation. We have also a portable version of that wireless testbed. You see it on the right bottom. So it actually is the same NUCs as in our main wireless testbed, but now they are battery powered. They are in some boxes, and you can travel with them and use them remotely. For instance, on left is an example in a shielded in an anechoic room to have some experimentation over there. All these resources or testbeds are available through the first Slices portal. So you see the URL on there. So you can create some accounts there and try to use them. We are also available, of course, in the open call, as already explained. This gives you an idea of the user tooling that we have. So this is called the JFET tool. So you start it up with the account from the portal, and then you see on the right you have some icons, so you can drag in some resources. You can interconnect them if needed. You can define properties such as, for instance, the software image you want to have on that, maybe IP addresses, etc. And then you can actually provision all the resources, and you have access through SSH. So on the left you see some more extensive examples of, for instance, software-defined networking examples with a larger topology, or at the bottom where we actually combine 2 different testbeds with a GRE tunnel. JFET has also some automatization possibilities. So there's also a CLI version besides the GUI version. And we have also defined experiment specification, the eSpec, which combines actually a description of the resources you want to use, also the files you want to deploy, and some scripts, for instance, Ansible, to set up your experiment. And that can be combined with, for instance, random passwords that are used, for instance, if you set up a cloud environment, so that everything is out of the box automatically. It gives back the passwords that have been set, etc. And to give an example of experimentation that has been done on the testbeds, this is a real example of a Belgian SME which wanted to have some some more explanation on some problems they were facing. So they develop passenger information systems for trains, amongst others, the Eurostar, as far as I know, and they had two problems. So the first one was if the software needs to be updated, they always got the question from the customer, how scalable is that? Can you scale, for instance, up to 10,000 cars? Is that possible? So they didn't know they cannot do those tests in the real on the real trains. So they asked, can we do something with the testbed? And the second one was they do handovers from Wi-Fi in the train stations to 4G, 5G on the tracks. And so they wanted to know what happened to their software. So what we did is the first one on the scalability of their software, of their backend. What we did is we used the virtual testbed. We deployed Kubernetes clusters on there, and then each Docker container was actually a train or a car, and we upscaled those numbers to see what happens with their software. And the second problem with the handover was done in our wireless testbed. So you actually see the mobile robot there with one of their own antennas, shark fins antennas on top of that. So we can actually put in some dedicated hardware in our labs. And there they did handovers between the Wi-Fi base stations and the 4G at that time. So there also they could learn what happens with that. So that's actually my last slide. So again, there's the documentation up and running. So if you want to use one of those testbeds, go to doc.ilab.imec.be. They are available to the portal of slices, so it's easy to create an account on that. And if you want to contact me by email, you can just use the email address on the slide. So thanks a lot, and this is an introduction to the IMEC testbeds in Belgium.
Okay, Brecht, thank you very much for your presentation. Let's continue now with the University of the Basque Country with a presentation regarding applying 5G and beyond to smart manufacturing with SN4I. Eduardo, I hand over the mic to you.
Okay, thank you very much. Well, I'm going to present a bit our infrastructure, which capacities it has, because some of them might be different to what you have been hearing up to now, and also what are the capabilities and what we expect them to have. We are presenting, in fact, two different kind of resources which are linked together. On one side, we have the Aeronautics Advanced Manufacturing Center. We will speak about it. It's a university center which is devoted to the research and manufacturing of very advanced equipment pieces for aeronautics, mainly for plane engines. And we have the infrastructure, which is the smart networks for industry, which runs over it. I will present the problem, the opportunity, and how it's been integrated. Well, we have been facing that deploying 5G and the associated technologies in an advanced manufacturing infrastructure has its outcomes. And we are targeting not only the 5G communication aspect, but also the related technologies. We found that in some of the cases, they are relatively new to the manufacturing external. Our objective is also to reduce frustration by managing the expectations. We want our industry to differentiate very clearly which is the hype and which is the reality. Develop a situational awareness regarding 5G technologies, because the best features are not available, and create an environment in which all actors of the ecosystem define a cooperative way to work. Well, what does this mean? This means that we are proposing a new way to experiment on both areas. First on manufacturing, and secondly on 5G and beyond applied to smart manufacturing. If we speak about a new way to experiment on manufacturing, we can say that the question that mechanical engineers have, I mean, how this process work on this material, which is the two-wear process, how this two-wear affect the manufacturing process, this is clearly a mechanical problem that we are able to solve through the network, because we have the resources to capture and process the data locally. We have the resources to share the data and manage the process remotely. And we are also able to provide the possibility to work remotely with international teams. That would be the way in which the mechanical engineering experts would use the resource. We have the opposite way. The opposite way is we are targeting the communication aspects, and the questions we are able to solve is it possible to interface this tool to the 5G network, satisfying requirements? Is what is available, which is being developed, able to go with the requirements? Is it possible to share all the experiment in real time, satisfying all the requirements? And this is good because we have access to real data. We have different protocols, different data capture requirements regarding frequency, bandwidth, with jitter. We are also able to show how this effectively affects the manufacturing process. Just a few words about the Advanced Manufacturing Center. We are targeting at the CFAA, we are targeting TRL 5 and 6, which is really dealing with real problems with real machines and with the real environments. This is the official, I mean, it's the kind of higher view of the system. Just to say, there are around 10 million investment, 9 million euros investments in equipment, and we have many of those. The interesting thing is that now when you say you are going to work with a robot, you are working with the real machine and not with a mock-up. And where you are using an interface, you are really using this kind of interfaces that are the one that control this kind of stuff. We have a great amount of machine tools, and we do research on this. This is the infrastructure. The financial infrastructure is able to deploy services through HCO OSM. We run over OpenStack and Kubernetes. We have had several edge technologies. Nowadays, this is no longer Inter-Smart Edge Open, but Kubernetes and other kind of technologies. We have a 5G coverage with NSA, with a small infrastructure, with a small base station for research, but we have also commercial coverage. We will support, I mean, we're still trying to get the right equipment, but the network itself should be able to provide URLC, but to tell you the truth, we're still working on the topic. Just to show you one of the use cases, we have been working with a company. This is the kind of equipment we have here. This is the equipment used to manufacture these low pressure rings for engines. Just to have an idea, this single piece costs around 100,000 euros. This means that having the good process, being able to do this field tree sort of tape fan holes is very demanding in terms of precision, and breaking something means breaking this part and means losing a great amount of money. We have very specific sensors which are sampling information from every millisecond to 2.5 milliseconds. The important thing is that most of the times we are not deciding ourselves which is the best sensor to use or the best solution, but normally many of these machines has a specific equipment to measure efforts, to measure accelerations, and they have their own requirement. Sometimes also you need to pre-process all these signals in proprietary equipment using proprietary protocols, This means that it's not so easy just to say we're going to put some kind of pressure measurement or whatever. I forgot to say this is the kind of information this equipment is sending. This means that you generate a great amount of data. This data needs to be treated. Some of them need to be processed before being stored, and that's the kind of thing we are providing. Just for you to have an idea of other things we have been done, we are running digital twins. Digital twins, you understand, it's a way to mimic the working of a bigger system and integrating it in a management process. And in this case, what we have done is we have been working to get to the management of a car equipment manufacturing. This means that here we are really dealing with forklifts that are being positioned, which need to measure the acceleration, the forces they suffer while crossing through the storeyard. We need also to device. We have developed a sensor to know at which height do we place the placers, because this is something which is normally not being offered by the measuring facilities of 5G. And this means that we are able to really propose this kind of things. I forgot to tell you, just I want to know. I will show you just the kind of equipment we have, because I forgot, and I think it makes a bit sense, because sometimes under a logo you lose the real size of the things. I mean, just to say, the first one, this is a lab that can manage equipment of more than 2 meters. You have equipment which has 80 kilowatts of power. I mean, you really see that this equipment is very big size. Every one of this equipment is in itself a network which has several requirements in terms of communication. We could go to every, I mean, this is available on the net, so you are able to take a look at it. We have additive manufacturing. In fact, this is one of the aspects in we are clear experts. And well, this was just to show you the broad range of possibilities we have regarding the machine capability. Okay. Which are the problems you can solve with this kind of infrastructure? How you coexist with the legacy protocols? We have most, if not all, the technologies regarding data communication. How we replace wires in moving platforms. How we manage the bandwidth, delay, and jitter, not only for measuring, but also for taking decisions in the manufacturing process. Is the integration with TSN possible, not only at the 5G level, but also at the processing level? We have many different things that are related to the information transmission. For example, one of the things in which we work particularly is in the slicing. And the slicing is not only used for performance isolation, because in this laboratory, it could happen that different projects, even for competing companies, are experimenting and are manufacturing pieces in the same yard. This means that we need to be very, very careful. We have also helped companies to decide if MEC is a good proposition or edge. Managing different kind of edge help them to choose the right one. We have been working also very closely in getting curated data. I mean, this is the kind of things which are problems that you can solve. Something which is very interesting is that we are helping people to manage the application lifecycle, because this is something that in OT is still not the case many times. We have worked with the concept of network service, but one of the things that appear when you go to manufacturing is that still nowadays, many of the supporting computers, the operating systems, are using non-Linux platform, mainly, for example, Windows. And we have been able to integrate these Windows servers into the network service and work with them. And this is we really think that our node, which is available right now and will be available through slices, is a compute everywhere fabric with a state-of-the-art high-performance manufacturing infrastructure. We're speaking that many important engine manufacturing companies are working with this, and that we are able to offer the best of the 5G technologies and beyond to the people that are used. One interesting thing is that, for example, using the paradigm of continuous integration as so an FB and SDN, once you run an experiment, you can really store it as a network service, and later, 2 months later, you can restart the service and just try another kind of material. You just can try whatever. Very important thing is that it's both connected to the Spanish REN, but also to the European Research and Education Network, which is JAND, which has a node on the university premises. We are now evolving the 5G coverage. We are integrated TSN at all levels. One important thing is that we are a team of mechanical engineers, but also telecommunications engineering. This means that we are able to solve both part of the problem. We can help researchers on the mechanical topics to run an experiment, to study some process in at very highest detail, and we are also able to capture that data in real time, to process it and give access to researchers that are not here. Our idea is in the future to have it as a part of the future smart manufacturing process, and not an add-on which is later built into the solution. Integration in slices, we will have many benefits. You can have some of them here. The interaction with other rating institutions in slices will bring the opportunity to work in topics like secure license, industrial cybersecurity, critical communications even beyond URLC, millivolt deployment in industry, mechanics processing, in-network computing, and other additional resources that might be used. I mean, we are not a cloud provider, but we have our own resources that can be used at least as a buffer for later processing. Nowadays, we are accessing it through VPN. We offer OSM instances over OpenStack tenants. We have several network services which are available, and we are even able, which is how we work with our colleagues now at the companies that are working with us, we can help them to prepare their own network services. I didn't put here a picture of the real network we have now, because there was some kind of proprietary information we were not allowed to share. But I could say that it's a rather important infrastructure. Of course, all the mechanical aspects, just in case you know somebody which is very interested in manufacturing, will be routed to CFIA. because they are really interested. And well, between the slicers, a full solution is deployed, and going forward to the VPN access, well, end of June, this facility will be available through FET4 5+ as a result of an open call. And well, this is all from my side. Thank you very much. And if I pass the floor. Thank you very much. If you have any questions at the end, as you prefer.
Okay, thank you, Eduardo. And now we are moving to the last presentation, but not the least by any means. This is from Eurocom area. Raymond, the floor is yours.
Okay, can you hear me okay?
Yes.
Okay, so I'm here with Walid Dabouz. So just quickly to introduce who we are. So my name is Raymond Knopp. I'm the head of the Communication Systems Department at Eurocom, and I'm also president of the Open Air Interface Software Alliance. And Walid?
Yes, hello. So I'm Walid Dabouz. I'm from INRIA, south of France, and I'm responsible of the Diana team that work on networking, and we collaborate with Eurocom on this wonderful project.
Okay, so thank you, Walid. So you can see in the picture, we're located in the south of France. So Fiantipolis is not too far from where the Cannes Film Festival is being held right now. So Walid, do you want to do the introductory part?
Yes, I will maybe do a very short introduction and then leave you the floor. Thank you very much. So, you know, we have been involved in for a long time now in building test beds and experimenting with wired and wireless networking within the OneLab projects, then Fed for Fire, FEET, French project. So several projects for maybe more than 25 years. And the question we were asking ourselves, would we like to continue working on this? And is there a need for a new test bed in this, I mean, after all what we did before? And what the answer we found is that there's a need from the telecom point of view, because if you take the cloud, a few years ago, or let me, people used to have their own servers trying to run an experiment or deploy new servers, but they need a huge investment to do that. So then with the cloud, people can design their experiment and then maybe run it on a larger scale very easily and maybe instantly, very fast. And the question we were asking ourselves, is it easy, or can we do the same for telecom network, for 5G, for 6G? And this is the question we wanted to answer. And because Eurocom has a long history in 4G and 5G, we try to team with them to build the Sophia node that you see now. Yes, here are Eurocom and in real locations, few meters. So we installed 600 gigabit per second fiber between Iot Lab, that is an anechoic chamber at INRIA, and between Eurocom, place where you have several type of equipment that will be described later. And now maybe I will present the last slide. Yes, this one. Thank you, Raymond. So the idea here, what is it? Is to provide resources, programmable resources that you can customize to test your own idea. So you come with an idea and we provide all the rest. We have radio resources like latest technologies, 5G base stations called radio units. Yes, we have Wi-Fi, we have user equipment. All these are like available and can be made available to users with different environments, whether in the anechoic chamber or in office environment or outdoor environment. So different possibilities to provide, to run those equipments and to provide you access to it. But not only the radio resources, also, no, please.
I'm sorry.
Yeah, sorry, the same one. Also some compute resources where you have servers that are accessed via switches that allow access to those servers, where you can run telecom functions, user plane functions, and other aspects that can run on those, let me say, compute clusters, whether for application level or for telecom-oriented functions that can run on those services. And the switches that you see on top of these servers, the white switches are data plane switches to access those compute resources, but you also have in gray the management switch that can be used to pilot this and control all these. The third box on this same slide is the programmable network resources, the software-defined fabric that you can build and run with, let me say, Tofino switches that are able to run P4 programs, and then to be customized, and then providing all type of let me say interconnections to the users. So all these are flexible. They are being deployed now. They are being tested with the latest software technologies that you see on the latest part on the right, Kubernetes, Docker, and all the ORAN family, SD-RAN, the different operating systems, etc. And then a big piece is the open air interface experience, and we are very happy to work with Eurocom on that, and we are getting more experience. We are able now to start deploying this technology with P4 switches in order not only to run your telecom functions, but also to program the, let me say, the switches to run like low-level switching requirements and provide this to users in near future. So I didn't talk about our previous testbed, Iot Lab. I just introduced this Sophia node we are building now this year and next year. And I leave the floor now to Raymond to give you more details about this. Thank you.
Okay, thank you, Walid. So I just want to give an idea here of some of the interconnections that we are currently offering and what will surely come in the coming years. So in the bottom right is the site that Walid just described, which is interconnected to Renater, to other slices nodes. So we can distinguish the ones on the European scale on the bottom, but also the other French slices nodes, which has a nice logo up there called Silex, which is about to be founded on the French level. But I think what's important too, and in the context of today's talk, are some of the other interconnections that we will have with the, let's say, more industry dominant world. In France, there's one very important national initiative called Engage 5G, which is run by Orange and by Brékine. The site in Sophia Antipolis has a VPN tunnel to this Engage 5G. So basically what that means is allowing experimentation also with some industry players in the French ecosystem. And we are aiming very much to be tightly integrated also into the SNS joint undertaking that Serge mentioned at the beginning. So the idea here is to open the slices sites generally, and in particular the one that we have in Sophia Antipolis, to allow interconnections with other initiatives which could be more industry driven. If we take a high level infrastructure view of the site that's being built now, and part of it is already built. Basically on the top, what you see are the possibilities for integrating services. So you have the possibility of providing a service to the site and running it. I'll give two examples in a minute. Another possibility is actually build the service on the computing fabric of the site. That is something that's happening actually in one EU project right now, where the partners are able to provide either Docker images or source code and build the overall service. So all of the necessary container images that get deployed on the infrastructure would be built by the infrastructure itself, in some sense, to optimize the resource allocations in that way. The site is actually also used for development and testing in various communities. So of course at Eurocom, we lead the open air interface initiative. So we actually use the site for all the CI/CD services for the community. Similarly for Mosaic 5G. We are starting now to provide O-RAN services so that people in the O-RAN ecosystem can test certain things on our facility. And we will also be a testing site for the Magma Foundation software packages, and that will some of the testing procedures will actually be running on our site. So there is a very significant CI/CD and testing framework in addition to experimentation running on this site in parallel. So there is the notion of orchestrating services. I won't go into any details, and of course network orchestration as well. The underlying compute and switching has to be seen as a series of clusters. These are not all completely configurable. Some of them are production clusters. For instance, the one I've noted here, Eurocom cluster number 1. That's an OpenShift cluster with a fixed topology. The cluster number 2 will be much more flexible in terms of the way you can configure it. There will be possibilities also to deploy some of the network resources off of this infrastructure, for instance, in hyperscaler clusters. So parts of the network could be deployed on an Amazon Web Service cluster, for instance. We also have the INRIA cluster that Walid's team is building, and what Walid didn't describe, the INRIA Fit R2 Lab, which is also under this the same umbrella. What's very important is the switching fabric. We are using primarily the ONF SD fabric. So a lot of it is based on P4 switches. So that there are a series of P4 switches at INRIA and at Eurocom, which are interconnected as Walid described. So we have an end-to-end fabric across the two labs. There are a variety of radio interfaces connected to the network today. Some of them, as you can see on the left, are national instruments, but others are commercial radio heads. So we have radio heads from Avenir, from AW2S, a French company, from Benatel, and also quite a few remotely controllable user equipment. So what you see on the left, the Quectel and SIMCOM modules, those are connected to PCs so that the experimenters can actually stimulate the user traffic. So that's from a very high level view, the way the site is organized. And what I thought would be interesting here is just to give two examples of how industry is using the site today. That's the subject of today's discussion. The first one is a running ICT 42 project called 5G Records, where we are offering a subset of the infrastructure that you just saw, so that our partners in the project can come and deploy hardware and software in the site. So this is actually an example of a local deployment, which is 100% in Sophie Antipolis. And it represents what I would characterize as a futuristic real-time audio processing service at the edge. So this is a cloud-native high-end audio processing service, which is developed by a company called Sennheiser. So anybody that's into high-end audio definitely knows who Sennheiser is. They make all of the microphones and speakers that are used in all kinds of different audio applications. And so what they're interested in is examining the use of 5G for real-time audio processing, in particular for either events like concerts or for studio recording in a distributed setting. So they want to study the low latency extensions to 5G as it pertains to their types of applications. So this project was proposed there are several use cases. This is one of them, where we use the infrastructure at Eurocom combined with open air interface. So you can see on the top, the cloud that I have there, it has 3 components in it. Basically what's called a DU, which is a part of the radio access network, which we use open air interface for. The other part of the radio access network, the CU, the centralized node, we're actually deploying software from a Belgian company called Acceleron. So this is one of their products in the context of Open RAN. So it's a cloud native telco component but that is not ours. So we've been working with them on deploying that in the infrastructure and putting an end-to-end 5G network together using Open RAN components. And on both extremities, we have the application framework that was provided by Sennheiser. So this is an example of using the infrastructure over a significant amount of time, and in this case, around 1.5 years, to test an end-to-end use case. So this is not a time-sharing type experimentation. It's actually deeply integrated into the infrastructure. A second use case, which I will accelerate here for you, is the one of O-RAN interoperability testing. So I mentioned at the beginning this Engage 5G initiative, which is run by Orange. Basically in Engage 5G, what we are trying to do is put together a distributed testing environment. So we're using the site in Sophia Antipolis, or a portion of the site in Sophia Antipolis, which is interconnected with similar compute in Paris. So we're talking about almost 1,000-kilometer link between the two sites. And the software is distributed across various clouds. And this represents what you can call a disaggregated radio access network, which is really the target architecture of the O-RAN ecosystem. So we're using a part of our site here in order to integrate with partners in Paris for doing end-to-end O-RAN interoperability. You can see the different interfaces that I listed here in red. Those are the particular interfaces that are being tested by this dual infrastructure. So again, this is another case that will set of experiments that will be running over several years that are sharing some of the resources in our site with partners in various projects. So I think that's really the end of my discussion here. What we wanted to show you was how we are building this site in Sophia Antipolis. And we gave 2 examples of industrial use cases for using the infrastructure. And now in the context of slices, we'll reach out to other industry players very naturally in some of the projects that will be built using the slices infrastructure, or on a point-to-point cases with some industry players. So thank you very much.
Okay, thank you, Raymond and Walid, for your presentation. This was the last presentation of our first industry day. I hope that we were able to provide you with an initial, let's say, description of what Slices is going to be able to offer in the future. So far, you saw that there are several test beds that can offer access to the industrial users in order to perform advanced research experiments. When Slices is completed, all of these different test beds will be able to accessed through a special portal so that it will be much easier for industry and industrial users to perform these experiments. If you have questions, we will always be available to answer them. And at that time, I would like to thank you all for participating, all presenters. Special thanks to Serge and Peter for their initial talks. And I hope to see you all in the second industry day that we will be organizing probably next year. Thank you all, and have a nice day and a happy weekend. Thank you.
Thank you, Kostas. Bye-bye.
Thank you. Thank you.
Bye-bye.
Thank you. Goodbye.
Bye-bye.
Bye, thank you.
Bye-bye. Thank you.
Thank you. Bye.